Can Zoom hear me now?
Yes, we can hear you.
Yes, amazing. Thank you. Right. So, yeah. So the organizers, okay, there are like old organizer. I think first is like Edward Truls and Kwan Mui, also Veve. Then me and Irji joined like sometime later. Then our like Italian branch, Fabio and Luca. And this year also Amy joined us for the mostly like she contributed to challenge and so like to the workshop. And we have our competition now sponsored by like academic institution, unlike all these times before when a company gave money, now actually CTU in Prague give money. Okay, so here's the plan. So now I will talk a little bit more like about the image matching and like what there. Then we have this block of 3 invited talks. Then we'll have coffee break. Then we have a paper talks. And then like most of them like should be doing live. You'll be able to do questions and answers. And like we don't do posters. And it's actually terrible. Like this way, other workshop I did, we do posters and it takes like 15 minutes to go there and then back, and then poster session is over. Yeah, so then after paper talks, we would have coffee break again. And then we go to our challenge, which is like, I don't know, like important part of the workshop every year with the challenge talks, which also they would be doing live, but unfortunately most doing in Zoom because of like time and these issues. And I think we have one video recording, and then we'll have like some closing session. Yeah, so 6 years. Like I think this year we were a little bit more selective. We have like much less accepted papers, and it's not because we had a like less submitted papers. It just like it happens that we were like super selective. Like maybe that's good, maybe that's bad. We did IGCV paper about image like matching how to benchmark in 2020, because like there were like many metrics and way how to do it, and like it doesn't align in the practice, because for example COMAP is like still the king, and like all these like nerves, Gauss and splitting, they need poses, and like usually these poses come from COMAP. But when you look at the other like benchmarks, usually, okay, the COMAP is bad, safety is bad. Like, no, they're not super bad, actually. Like, they're great, probably something is metric. So we published a benchmark and the data set like this many years ago. And like since then, we don't publish papers, we trade on competitions, Kaggle, but like this year, we actually plan to do one more paper and do like one more data set, hopefully like bigger, to actually go a little bit back to like standard academic setting. And like I think all the live streams from the previous workshops are available. If you're interested in something, like you can go check. And then for like competitions, usually they're like I do recaps for every competition on my blog, and then like they're on Kaggle and like many things. So like I also tell my students to like if they do image matching, just check workshop materials. Yeah. And so what is this workshop about? Like we like have like local features and beyond as a subtitle. And the thing is like we want to do like rigid matching. We want to reconstruct rigid objects, which like now we have like many like deformable things and tracking and but actually we believe that SFM and like 3D reconstruction from images is far from solved, like very far. What is solved is like current data sets, which were actually created many years before. That's why like they become easy. But the data set become easy doesn't mean that the problem become easy. And there are also like new ways how you do this. And okay, we show these slides every year. So we were like last things which are not consumed by deep learning. Yeah, but what is funny is that although there are more and more deep learning like or learned features, like for example, and super glue, like amazing approach, which like blow up like our leaderboard in 2020 and is still used until now. But this is only part of image matching and SFM solution. And like, what about the whole system? Well, people use column people use geometry, people use these like classical things. So maybe deep learning is like still haven't eat everything. And maybe like next year we say, okay, we cancel workshop. So hey, GPT, 3D this, all done, we are out of business. Maybe. I don't think it will happen. Yeah. So, and still now they're like, now 3D is like very important thing in the current CVPR, and like I really glad because okay, diffusion is super cool. I'm using this, but like my heart is in 3D, and like I really love these Gaussian splattings and everything, and they are built on the image matching. But like besides, we have all this topic. Like if you check social media and everything, so we have nerves, foundational models, and like that's it. Like you don't hear about anything else. But actually, there are like more cool things. And one of the, like, actually, we have two recent cool things which use deep learning for SFM part, which is like super cool. Like, finally, we have like all these learned features maybe matching, but SFM is PyCon. Maybe not anymore. We have DUSt3R, which is invited talk and also challenge participant. We also have VGG-SFM, which is one of our winners, third place solution, like really great work. We have and A0 from Niantic, which did not participate in challenge our workshop, but we hope that they do next year. So, and maybe next year we actually would be fully consumed by deep learning solution and actually be able to go forward from the coma. Yeah, and like, and maybe even if we have all this cool stuff winning challenges, another thing is production. Like Google Live View and like still things, they still use this for large scale, and this is because it's so very efficient. And what is funny thing about like classical thing versus deep learning, so like VGG-SFM, when the author was first trying to run it for our challenge, he could not because of out-of-memory error. Like he could train this on A100, but could not run it on T4, which is like standard machine on Kaggle competitions. And while you can say, okay, T4 is very old, but it's also cheap, and for like scale, you need to be cheap and fast, and it's also like very long way to go. Yeah, and we iterate on our challenge. I would not go in and do this. So this is like a little bit recap of those of you who didn't know. So these are like standard academic challenge, more or less. We have website, evaluation server, like 13 team, 20 team, 100, and then in 2022, we moved to Kaggle. Yes, and since then we are on Kaggle. We are super happy about this in terms of like people participating, and all the time, like in all things, actually people who were not working on 3D but working on deep learning and engineering, they were like among the winners. Actually, proposing some maybe better solution than academics, which I believe also exciting. But on the other hand, they were using solution proposed by academics, and some academics were also among winners. So this is like really how it should be. And like this year, we have like not just SFM thing, but we have like hexathlon. So we have now 6 different categories, which we would cover later. But like they are like super different, like transparent objects, like repeats, nature scenes, because before we were like considering all like phototourism, urban, like, you know, now boring stuff. Yeah. So, and like we do the SFM. One of the issues of Kaggle, though, is actually hard to run SFM within the Jupyter notebook constraint on Kaggle. Like it's hard to compile, it's hard to run, and like we like acknowledge these difficulties. But I think for at least for a while, it's definitely worth it to go and have this much wider community there. And hexathlon here is like some examples. So we have seasonal changes, we have illumination changes, wide viewpoint changes as usual, like some transparent repeats. And like what's more interesting is actually some of the scenes, especially in test set, combine all these, maybe not all, but many of these challenges together. For example, the scene is nature scene. It also contains repeated structures such as very similar trees, and it is from the winter and summer and autumn, and also it is at night. Like no method can solve this, which is exactly what we look for. We're trying to give a like North Star to people to work on SFM. Like, no, it's like not getting this latest like 99.999% accuracy. You can actually improve things like by order of magnitude from 10%, hopefully to, I don't know, 80 or something. And what we hadn't changed since here, we still have this great prize fund of $50,000. One more shout out to like our Italian part. Like I think that was like Fabio and Luca who bring this cultural preservation thing, especially that some of images in our dataset depict objects which unfortunately do not exist anymore. So maybe these images are like one little way how to preserve it, maybe some like rebuild this, although it would not be the same. But I think it's also good to have like some like more cultural thing. Yeah. Kaggle challenge sponsors Google as always, and now our university gave up a lot of money, so thanks to them. And yeah, so I think I'd like to ask next speaker. No, come. Let's, so yeah. So come here, you would need to connect to Zoom.
Oh, should I connect to Zoom?
Yes.
That's interesting.
Yes, and video as well, please.
And video, okay. Sorry? Does that look good? So I think I'll get started. Do you think that's okay? So this is so amazing. It's really good to see all of you. Hope you're having a good day so far. And I'm going to talk about, I don't know. I'll talk about a new data set that we've made called MegaScenes. And in general, some of the challenges in 3D reconstruction at scale. Okay. But to start things off with, I am a huge lover of architecture, I guess I would say. I love cathedrals. And I remember when I was a kid, I saw this book called Cathedral by David Macaulay. It's this amazing book that I guess if you picture yourself as a person living, I don't know, 1,000 years ago, and you want to spend 100 years or more building a cathedral, this walks you through all the steps. So it shows you like, okay, here's all the tools you need. Here's all the craftsmen that are involved. It's beautifully illustrated. To start with, you have to dig some big holes in the ground. You have to cut stones and lay them in for the foundation, et cetera, et cetera. At a certain point, you make some progress and you have to construct this huge wooden wheel and you have to like raise it up to the top of the cathedral so that you can raise blocks up to the top. And you start to realize that it's not just the shape of the cathedral. Everything has a function. Everything has a reason for why it is that way. Everything has a name too. To me, it's really amazing to see how this all works for real buildings. This really instilled an interest in architecture and also an interest in like, or an obsession maybe with reconstructing things. Okay, here's another book that is really, I came across more recently called The Story of Buildings, with these beautiful illustrations by an illustrator called Stephen Biesti. And in this book, you find illustrations like this. This is just amazing to me. This is the Notre Dame Cathedral. Why is it so cool? Well, it's just this beautiful cutaway diagram / exploded view diagram. You can see the inside and the outside of the cathedral. You can see like things split apart like the roof, so you can see inside of it. You can see people for scale. And you can see everything is labeled, like everything is semantically rich. Now, this is the kind of reconstruction I would love to create with computer vision. And also have it like know the names of everything. Like it could point, these names to me are very romantic, like flying buttresses or vaults or these like parts in the front that are the tympanums and the archivolts. It's just so rich and it reflects a real, deep understanding of what this building is and what it is for and why it exists and what the parts are for. Okay, so I think my current interest in life is automatically reconstructing 3D models of all the world structures to the richness of that diagram that I just showed you. And ideally from open data, right? From all the photos on the web, all the information on Wikipedia, and so on and so forth. Information that's freely available online. And we can do parts of that today. We can generate shape. So this is like a coal map style reconstruction of the Notre Dame Cathedral from many, many Flickr images with your camera poses and your point cloud. But it's, it seems like just a step towards that problem. So, and we can do better than point clouds too. So I'm about to show you something that the author gave me permission to, but I don't think this is online yet. I don't think this is even an archive, but so I used to show Nerf in the Wild as an example of what's the state of the art of how well we can create photorealistic renderings of data from internet collections. But I think this is a Gaussian splatting based version of that. Sung Yeo Peng showed this to me and said I could show it. So I think this is okay. I don't think it's online yet. But this is just so I think this is like a Gaussian splatting based reconstruction of the Trevi fountain from lots of internet photos. And it also allows you to control the lighting. So in some ways, we've come really far. In some ways, we still have a long way to go. But I feel like maybe in the community, or at least parts of the community, there's a feeling that 3D reconstruction is solved. You can just run Colmap and, I don't know, Gaussian splatting on data. It work well all the time. If it's solved, you can kind of reconstruct the entire world from internet photos. Maybe we're about very close to being done with this vision of, that I led out of reconstructing every scene richly from internet photos. So, there's sort of a question, people like me who like to reconstruct things, is it time to retire? What's left to solve? I remember in my PhD thesis, actually, when I was defending my PhD, someone asked, okay, well, it looks like you solved the problem of like phototourism. What do you do next after you reconstruct everything? And I didn't have a good answer for that then, but I think I have a good answer for it now. Okay, so the first thing you realize actually is that, okay, so we've been embarking on this project of reconstructing everything, and I'll talk more about that. That led to this MegaScenes data set that I'll tell you about. But of course, maybe it's just obvious in retrospect that once you start running a tool at scale, like hundreds of thousands of times, you realize all the flaws in it. Like once you start running Colmap at scale, you see all the ways that it breaks. And it turns out, well, I guess the biggest way it breaks is if you don't get a reconstruction at all, because there's not enough visual connectivity. But maybe the second biggest way that it breaks is repeated patterns and symmetries. And so if maybe you go to London, you see, oh, this is a beautiful cathedral, St. Paul's Cathedral. I'd love to reconstruct it. Okay, so you get a bunch of photos of it and you run Colmap on it. And it turns out you get a reconstruction like this. Okay, so what do you see here? Okay, so there's we have this dome-shaped point. We have 3D points in the shape of a dome. That looks good. There's a big dome here. And then we have cameras, okay, reconstructed cameras in the shape of a dome. That's good. Probably people are taking pictures from the dome, but these are not in the same place, right? Like you'd expect these to be co-located. And what went wrong is it's pretty clear from looking at this that this building has so many symmetries and repeated patterns. I don't even know the fold of symmetry of the dome, but all the sides look alike. That is just unable to disambiguate all those ambiguities and create a good model. And this is not just a one-off problem. Every building in London, I think, suffers from this problem, and lots of buildings in lots of other places too. This kind of visual ambiguity problem. Okay, so we set out to solve this problem because it was really annoying, and it really felt like this is a big hindrance to reconstructing everything in the world from internet photos. And we're not the first to try to solve this problem, but this visual disambiguation problem has been around for a while. But I think it's an instance of a very interesting kind of fundamental philosophical computer vision problem of visual twins, of things that look alike, but are not alike. It's almost like, yeah, it's very, very philosophical. So here's two images that look the same, but aren't the same. They're actually opposite sides of the Arc de Triomphe. And if you run your feature matcher, whatever feature matcher you love, it's going to find lots of high confidence matches, and it's going to think that these are the same thing because all the structures on the top look very, very similar, etc. Okay, so like I said, there's other things in life that look very similar to each other, but are not the same thing. So I remember this was 12 years ago, I guess. I was thinking about this visual disambiguation. Sorry, my mic seems to have gone off. I'll just try and hopefully you can hear me. I was thinking about this visual disambiguation problem of structure motion, and I came across this very interesting National Geographic article that was about twins, and the subtitle is Alike but Not Alike. And it made the point that I hadn't really realized before, but nominally identical twins are not actually identical for many reasons. Like in this case, like probably the pattern of freckles developed independently. It's all like stochastic, so that's different. But over time, especially as you age, as identical twins age, I think they start kind of diverging a bit from each other, and you can, the nose might be slightly different. They start to develop these differences that make them not identical. And it's kind of the same with like images of architecture too, like, oh, maybe, two sides of the building will have different like smudges of dirt on them, right? So we should be able to tell apart things that are alike, that look alike, but aren't alike. Anyway, that's just a problem that I've been intrigued by for a while. And so one name for this, sometimes you have twins that are identical, sometimes you just have doppelgangers, someone who looks like you. Maybe someday you'll run across your doppelganger, just who happens to be identical to you, and it's very fun in these articles. But it's not so fun when you run structure motion and they cause you to completely get the reconstruction wrong. Okay, so for this fundamental vision task of same or similar, it's not just philosophically interesting, but it's the difference between, these doppelgangers or evil twins are the difference between a good reconstruction and a poor reconstruction. So, okay, now how do you tell them apart? Well, if you're a person, you might say, okay, I'm just going to stack them on top of each other and blink between them. And now it's like a spot the difference game. And indeed, if you do this, you can see, actually, they still look kind of similar, but if you kind of look carefully, you'll see the statues here, these sculptures are different. The buildings in the background look similar, but they're actually not the same. They're different. You can tell them apart if you look carefully enough. And yeah, probably like each of these individual bricks, one of these images is pretty saturated, but you could probably like inspect like bricks and see, oh, this brick is different from this brick. They must be different structures. And it's very interesting. It's like the opposite of what we usually think about in feature matching or image matching. Like in image matching, we're looking for like positive evidence of, okay, these images are matching each other. And you usually do that in the form of finding lots of SIF features or LoFTR features or D, whatever features that look similar. But here you're trying to do the opposite. You're looking for evidence, evidence that they're not the same. It's like negative evidence of them being matching. And that's something we don't think about as much, but I think it's very important. Okay. So, okay, we did the classic deep learning thing okay, first we have to build a data set, and then we'll train a classifier once we have that data set. But it was very difficult to build a data set of these doppelganger pairs, these spurious matches, because even a person might have trouble telling, oh, is this the same side of the building or a different side of the building? So we relied on, I guess, the wisdom of the crowds to do this for us. There's a website called Wikimedia Commons. This is a sister site to Wikipedia. It hosts all the images that appear on Wikipedia and a lot more images besides. And it's a very cool website that, again, is like underappreciated in computer vision, I think, unless secretly all the companies are like using all this data. And what it has is categories of things. So of course, I guess like Wikipedia, this is all crowdsourced. So people who love to categorize things, I don't know, maybe librarians, who knows, they have curated Wikimedia Commons to be a semi-organized resource of visual content. So there's a category in Wikimedia Commons called cathedrals. And under that category is every cathedral known to Wikipedia. For instance, there's one for the Notre Dame Cathedral. And you could get lost easily looking into this data. It's so rich. You can find a subcategory that's historical photos of the Notre Dame Cathedral. You can find categories that, I don't know, archaeology of the Notre Dame Cathedral, views from the Notre Dame Cathedral. And you can even find things like a category of the organ and a category of subparts of the organ, like the chamads, which are the pipe organ pipes that point out horizontally. And I don't know, it's very lovingly crafted webpage. I love it a lot. Anyway, among the things that people categorize on Wikimedia Commons is viewpoint. So you might find in certain categories, like the Arc de Triomphe, a categorization of, into which angle they viewed that from. So someone carefully determined which angle these images were viewed from and categorized them accordingly. And if you see a subcategory that's named back right views of so-and-so, and another category that's front right views of so-and-so, then you can reason about, okay, those should not overlap each other. They should be visually disjoint sets of images. And so if you then match images across those categories and find lots of geometrically consistent feature matches, then aha, this seems like a doppelganger. I'm going to put it in my doppelganger collection. And you can run that on lots and lots of collections and find many doppelgangers that way. Now you might say, okay, well, this is kind of silly. Why Street View and things like that are categorized by viewpoint, but I'm, there's a part of me that wants to do everything using open data. And if we can do it with internet data, then I'm very intrigued by that. Okay, so we use this idea of like viewpoint categorized categories to build a data set of 76,000 images with 1 million image pairs and 178,000 doppelgangers. And here's some example doppelgangers that show you different places that where like the front and back are kind of similar but distinct. You can tell like, oh, this can't be the same viewpoint of the Alexander Nevsky Cathedral because this dome is in the wrong place. Even Walt Disney Corporation, maybe they're very obsessed with standardization. They built the same castle in 2 different Disneylands. One is in Japan and one is in Florida. So yeah, you get like matches between those that are clearly, these are thousands of miles apart. They can't be the same structure. And you could probably tell them apart by looking at the background. Like one has a mountain, one has, I think, a nice Florida sky in it. Okay, so you can find lots of doppelgangers, and this is great. You can then turn a classifier to determine whether a pair is a doppelganger or a good pair. There's some thinking that goes into doing this. Actually, I'm very curious. I think we tried using ChatGPT to solve this problem. It's surprisingly good, but I think not as good as our classifier. Anyway, just a bitter lesson is that like ChatGPT can solve a lot of the problems we used to think are hard. Okay, anyway, so what we did is not that, but we give a classifier the image pair after first having matched them. So we provide it with feature matches. Here's the location of features, here's the location of matches, so that I can reason about things like, oh, I see there's a lot of matches in the top of the building, but not the bottom. Well, what's up with that, right? And can make determinations accordingly. We also align the images with the affine transformation using the feature matches. So it gets to like easily compare, kind of flipping between the 2 images with corresponding points to look the same or not. And then you feed that into a classifier and, output yes or no. This is a good match, or this is a true pair or a bad pair. Okay, so let's see. So we evaluated this. Of course, we kept some secret landmarks that the classifier never saw during training, so we get a good test set. And here's the performance of just how well can it tell these images look the same versus these images are the same. Okay, and so we compared it to some baselines. Like the obvious thing you can do is just count the number of matches you get and threshold the number of matches. Like if you have more than 100 SIF feature matches or whatever the right thing to use is these days, you say it's correct. If it's less than 100, you say it's incorrect. And so those baselines seemingly perform pretty well. Our trained classifier is this blue line here. It gets about 95%. And you can say, oh, that's not a big improvement. Why are you so excited? Well, okay, the problem is, here's how you're going to use it. You're going to take this classifier, you're going to take your graph of image matches that you got from Colmap or whatever structure motion system you're using, and you're going to classify each edge as good or bad. And you're going to try and prune that graph of bad edges, and then you're going to reconstruct what's left. And even a single bad edge could screw up your whole model, right? So you really want to be very good at detecting bad matches. And so, 95% is much better, it turns out, for this task. You can see some examples of correctly classified pairs. Here on the left, we have negative pairs. So these are doppelgangers. And you can see that, okay, maybe something interesting is that it's very confident that this is a doppelganger. It gives it a low score. That means it's a doppelganger. It's very confident that this pair is a true match, and that's correct, it is. And it's able to do that, but despite these images maybe seemingly looking much more similar than these 2 images, right? In terms of illumination and other qualities. But of course, it's been trained on diverse enough data that it knows the difference between illumination changes and scene geometry changes. Now I say it knows that, I just assume it knows that because it's able to do this task. I don't actually know what cues it's using to do this. Maybe there's some secret like watermark on all doppelganger pairs, who knows? Or maybe or maybe it's using sun direction. There's many possible cues it could be using. Okay. Now, so then you can use this, as I said, to prune the graph of all bad matches or all matches the classifier deems as bad, and then run structure motion on what's left. And you get some pretty, okay, yeah, filter the match graph, run reconstruction motion. And so here's some before and after comparisons. Here's the Arc de Triomphe. You might say, this looks like a fine reconstruction, I don't see any problem. But what it's done is only reconstruct, this is vanilla coal map. It's only reconstructed one half of the building, whereas there's plenty of images to go around on all sides of the building. So it's just, spuriously glued both sides onto each other. Whereas after running doppelgangers, it works much, you get a full 360 reconstruction as expected. Here's another, this is that Alexander Nevsky Cathedral, which vanilla coal map produces, I think, one too many domes because it's getting all confused and discombobulated. Our reconstruction corrects that and builds a correct model with the correct number of domes and images on all sides. And here's some other examples. So I think the what did people say? Like the IMNIS challenge or I don't know, the ImageNet. The ImageNet of 3D reconstruction is Big Ben, like the canonical bad example. Big Ben is something which has four-way symmetry. It's very confusing to reconstruct. And it's not obvious this is broken, but all these models that are from vanilla coal map are broken in some way or another. And if you run our disambiguation first, you get much better results. Again, I think if you were to remove the cameras, you'd see a correctly four-sided Big Ben bell tower here. Actually, I think Big Ben's the name of the bell, but people call the tower that anyway. Okay, anyway, sorry, random. Now, I should say I'm very proud of this work, but Dimitro, I think, gave me some information that for the image matching challenge, it turned out that this doppelgangers didn't work that well. I can believe that. So we've also done some tests that suggest that it works better on internet photos. Weirdly, well, maybe not so weirdly, but it seems to work better on internet photo collections like the ones I'm showing you as test images, test cases, than on your run-of-the-mill images captured by the same photographer. I don't know exactly what is in the image channel, what the distribution of images is, but I think it's biased by what we've trained on to kind of these landmark internet photo collections. It hasn't, for instance, seen a lot of office buildings, I think. So actually we're training something newer that I think might work even better than this initial version. Okay, I thought I'd give that caveat. Thank you for the feedback. Okay, good. Well, now at least we have something that works on internet photos more robustly than vanilla cold map. And so now we can set about this project of, run it on everything, build 3D models of everything that Wikipedia knows about. And so that's what we did. I don't know, what's the right way of saying this? We have this ancient cluster at Cornell. By the way, this is Cornell work from Cornell students led by Joseph Tung and Jean Cho. We have this ancient cluster. It has hardly any GPUs. The GPUs it has are 5 generations old, but it has tons of CPUs. And that's perfect for if you don't care about CoalMap running as fast as possible, we have many, no one uses this cluster. That's the beauty of it. All the GPUs that we have that are new are kind of constantly being used by everybody, totally oversubscribed. We have this nice cluster of CPUs that we've been running, secretly CoalMap on for many months. And we reconstructed this data set called MegaScenes, which is over 100,000 structure motion reconstructions from around the world, consistent over 2 million open licensed images and registered images. These are only images that got reconstructed. There's many more images that are not reconstructed. Now, I think another thing Dimitro might razz me about is, well, it's 100K, that's not mega. You need 1 million to be mega. But okay, that was true of our megadepth paper too. But the problem is there's no good Greek. If anybody knows a good Greek prefix for 100,000, please tell me, because I can't find one. I did a lot of searching, but I can't find the canonical Greek prefix for 100,000.
Hectokilo.
What's that?
Hectokilo.
Hectokilo, is that right? Interesting.
No,
Okay, so we kind of rounded up and we're calling it MegaScenes, okay? And it's just, you can...
images is
Yeah, okay, the number of images is mega. Okay, so maybe it's poetic license, maybe it's okay. Anyway, it's certainly orders of magnitude larger than, kind of the previous data set that's kind of like this is called megadepth. Much bigger than that. Okay, yeah, order of magnitude larger than megadepth. Sorry, my screen is not totally in sync, so I'll have to keep looking at this screen. So, an inspiration for this is there's a group from Google who did a very similar thing, but in 2D, no 3D. So there's this data set from a few years ago called Google Landmarks Dataset V2. This is a data set for landmark recognition and retrieval. So it's like recognize if you're looking at the Eiffel Tower versus, oh, I don't know, the Louvre, or one of hundreds of thousands of other categories. Okay, so just 2D instance retrieval. We use the same source of data as they did. And we used data from Wikimedia Foundation, just exactly what I was telling you earlier, with a few different pieces thrown in. So if you want to reconstruct everything Wikipedia knows about, first you need like a list of those things. And the way to get a list of those things is to use a sister project called Wikidata, what is Wikidata? So it is a kind of knowledge graph, like Google has a knowledge graph. There's these things called knowledge graph, which kind of are encyclopedias of everything with connections between them. So this Wikidata is a big database which has, for instance, a category called tourist attraction. And you're then able to do an API query that will enumerate all of the tourist attractions that Wikidata knows about, everything from the Acropolis and the Antwerp Zoo to whatever landmarks start with Z. I can't think of any offhand, sorry. But there's a lot of them. And then for each of these categories of here's a place, you can then go to Wikimedia Commons, like I told you about earlier, which has all these images indexed by subcategories, like Berlin Cathedral and all the subcategories underneath it. You can download all the images underneath that root category. And then you can run them through structure motion with doppelganger step thrown in for models that are ambiguous. And you get some nice structure motion point clouds and registered images. And you run this enough times and you get 100,000 3D models. Here's a visualization of some of them. And by the way, I think this just came live yesterday and the paper will be in archive today, I think. But the data is now open, the website is live, you can start downloading data and using it. Here's just some visualizations of some of the models in the data set. Again, it's not just your like Notre Dame cathedrals of the world. It has a very heavy tail of lots of different places that you might be unfamiliar with, as well as the famous ones too. I guess if you wanted to be critical, you could say, okay, to a first approximation, this is a data set of religious buildings, because that's the most common thing on Wikimedia Commons, but it has a lot of other stuff too. It has bridges and I don't know, tombs, lighthouses, etc. This is just a count of the number of scenes by the category, the Wikidata category. And also to a first approximation, it's a data set of European places. This is a heat map over the world of where these landmarks come from, because they're all geotagged. That's another thing Wikipedia knows about. So it's heavily biased geographically, but it does have, at least worldwide coverage to some extent. Okay, so yeah, I don't know. I encourage you. I'm going to show a live demo actually, if I can. So okay, we had our undergrad research assistant Brandon build a nice web viewer for this. So it's like a Colmap viewer on the web that you can explore this data set. So I've preloaded a few. Okay, so you can start typing in this box and it will autocomplete the name of different landmarks. This is like that famous Sphinx in Egypt. This is one of the first things I reconstructed in my life, actually, when I was a grad student. It still works. That's good. What is this? Oh, it's okay. Here's some cameras. Okay, this is another Sphinx. Okay, it knows about other Sphinxes in the world, like there's one in the Louvre. Okay, that's nice. So it has museums. Okay, surprise. I don't even remember what oh, this is that Kapellbrücke, this famous bridge in Lucerne. So, outdoor scenes. I preloaded, this is the Pantheon, but not the one in Rome. This is one in Paris. It has indoor scenes, as you'll see in a moment when I think the point clouds are a little lagging the cameras, maybe because there's so many points. Okay, anyway, you see where the cameras look like in the inside of the Pantheon in Paris. Okay, I'll move. Oh, there they are. There's those points. Yeah. There's nothing more that I love than a good point cloud, even if it's kind of sparse. I just love it. Anyway, I said there's a long tail. So I don't know, this random address in New York City, 11 West 54th Street, must be like one of those buildings on a historic registry. There's a point cloud for that too, with cameras registered. In fact, cameras that you can see are taken on the opposite side of the street and things. Anyway, yeah, you can just go here, a Space Needle. I'll just get that. You all know what that looks like. Yeah, you can start typing. I don't know. Does anyone have a landmark they want to see? Anything come to mind? Yeah, oh, do you have a suggestion? What's that? Okay, CN Tower. Okay, yeah. Oh, so yeah, you'll see it like autocompletes for you. There's a lot of interesting landmarks here. CN Tower. Now I haven't like inspected all of the landmarks, so I can't vouch for all the quality, but we'll see. Okay, it should load, right? Let me try again. There you go. Oh, and yeah, of course, like I said, the other problem with ColMap is that okay, so this is, okay, the points should appear in a second. I think you're looking at like Toronto. Maybe this is probably the top of the CN Tower, views from the CN Tower. Is that right? Does that make sense? Okay, yeah. So there's other components here. I don't know, a lot of them are kind of small, like this has only 39 cameras, so this might be kind of unrecognizable. Some other, oh, yeah, maybe some other view of Toronto from some other part of the, I don't know. Anyway, what's that? Oh, maybe this is the island looking towards the CN Tower. Okay, so yeah, I mean, like I was saying, with ColMap, you never know what you're going to get. You often get models broken into sub pieces, like the inside of a scene and the outside of a scene. There's no visual connectivity, so they won't register together. Actually, that's something I'd love to work on more, is like, how can we reconstruct like full reconstructions, even if like we don't have visual connectivity between all of the parts. There's this nice paper called 3D Jigsaw Puzzle, I think Ricardo Martin Briola. I see Rick in the audience, like maybe he was a co-author, sorry, I can't remember all the authors offhand, but that explores that problem. Okay, thank you. Good. Okay, so that's just a taste. You can play with it yourself. Now I have to say, many of the landmarks are super small, like 2 cameras, so not all of them will be as beautiful as that CN Tower. But what we lack in all of the landmarks being amazing, we kind of make up for in, we just have lots of posed cameras for very diverse places in the world. Okay, good. So, I guess maybe the implicit problem behind all this is, just if you're enumerating open problems is, what do we do with all this 3D data? I think you can do all the things that you can do with data sets like megadepth or phototourism data sets. You can maybe learn better feature matching because of the scale of the data. Maybe, so we don't have dense depth maps, but that's something we're working on adding to the data set. Maybe you could learn great monocular depth prediction if it's not already solved. This kind of data, especially if we have dense depth maps, you could train a better duster, I would imagine, with this, or any kind of geometric 3D reasoning task. And just, I think, it'd be great to see all the ways people can find uses for this data. I like this data set a lot and hope it can get some usage. I guess I'll talk about one particular application that we described in the paper, which is view synthesis. Sorry, and I talked about, his talk has heavy overlap with the talk I gave earlier at this AI for CC workshop, and it will also have a lot of overlap with the talk we'll give at a UMD 3D workshop in a few minutes. So, you can just go to one of them. Anyway, so I'll just quickly, because I have to end at 2, is that right? Okay. You know what? I'm actually going to, because I think I started a little late. I'm going to, I'm just going to say, we can train 0, 1, 2, 3. You all know 0, 1, 2, 3. It's like, you can train view synthesis using posed images, right? So you give it an image, you want it to render it for a new pose. You condition a diffusion model on that new pose, and it can do this task very well after fine-tuning stable diffusion. It doesn't work very well on scenes because it's been trained on object data from Objaverse. But if we fine-tune it on this MegaScenes data, it works much better. I think I'll leave it at that, and just, you can, if you want the details, I'll talk about, you can come get me later or read the paper. So I'm just going to skip, I'm very sorry, I'm just going to skip through this whole section. I think I'll just show some pretty videos. You'll have to bear with me for like
7 minutes for questions.
Yeah, I have 7 minutes. I know. I just want to leave. Yeah. Thank you. Thank you. It seems like my computer's frozen though, so I'm gonna try and. I might spend 7 minutes like debugging, who knows? Oh, there we go. Okay. So I'll just show some results. If you take kind of a method that's not been trained on scenes, this kind of a variant of 0, 1, 2, 3 that's been trained on more data called 0NVS. You don't get, so the idea is to render a trajectory shown on the upper right corner, starting from a single reference view. So single view to novel view. Things that haven't been trained on this kind of data, on scene level data, don't work very well. But if you fine tune these view synthesis models on MegaScenes, because after all, one of the other things that this data set is a massive data set of posed imagery. You can train view synthesis models very well with this data. And if you further condition on this warped image conditioning that I'm showing up in the right corner, it gets even better. I'm going to just skip over the details so that there's some time for questions. Okay, now I just want to talk about some open challenges. So one open challenge is, as I said, the ambition here is not to reconstruct just geometry soup or point soup. I think the ultimate ambition is to reconstruct things that have the depth of information as this illustration, right? Things that know about the names of things that know the function of things that can simulate what people do inside of this building. I think 3D reconstruction is very far from that goal. But I do think that, and sorry, my slide is partly occluded by the Zoom. I do think that it's clear the way the field is going. People are training larger and larger models, and models that are capable of more and more things. I think a very obvious idea is to try and train some kind of model that combines vision, language, and 3D all in one by taking the fact that MegaScenes exists in this rich context of knowing everything that Wikipedia knows about. I think there's an opportunity to kind of, structural for motion has been kind of separate from all the work on large language models and so on and so forth. But I think maybe there's a way to integrate all these things together. And maybe it's time to do that. Just to show, one nice thing about data on Wikimedia Commons is that it has captions and language. So in addition to reconstructing 3D, you have this semantic information. Like, okay, who knew this thing was called a Strix here? Wikipedia did. Okay. So, eventually, I don't know how long this will take, but I feel like it seems to me the right thing to do as a community for people who care about structural motion is to rethink the whole CoLMAP pipeline. And we're starting to see that with things like A0 and FlowMap, work that are rethinking CoLMAP. But I think we're not quite thinking big enough, because what I really want is, there's so much data beyond image data. There's text, there's maps, there's floor plans. There's all sorts of rich multimodal data that we can use for reconstruction. If you feed CoLMAP a floor plan, it will just discard it because there's nothing you can do with it, right? It doesn't fit in the classic feature matching paradigm. Despite a floor map being or floor plan being, if anything, the most useful image for understanding the structure of a building. Okay, so, how to fuse all these different threads in the computer vision community together is a big open problem. Another big open problem is reconstructing 4D scenes, 4D, not 4D, 4D, 4-dimensional. So, Notre-Dame Cathedral is a good example. There's the tragic fire there in 2019. We need to be able to reconstruct things over time. We have some work on this called neural synchronology that I'm just going to skip over because we're almost out of time. So there's lots of progress on 3D reconstruction happening. A lot of it is actually driven by better image matching kinds of technology. But I think what we're missing, some of the big open challenges are complete models, like the inside and outside of a building together. Semantically aware models that know that something is a flying buttress and know how you can interact with scenes. Sort of what the next thing beyond CoLMAP is, how to transcend that paradigm, and we're seeing work like that already. And beyond just geometry, but fully graphics ready models that can be relit and interacted with. I can go up and light a candle inside the cathedral. 4D reconstructions, both over scales of years, but also I've reconstructed the Trevi Fountain many times in my life, but I've never reconstructed a version with people milling around and water flowing. There's lots of kind of dynamism that's lost in 3D reconstructions. And I think generative 3D scenes is also a clear open direction. Scene level generating a million cathedrals like the Notre Dame Cathedral, and as detailed as that, but are new and imagined. So thanks to all the people who led this work and collaborated on this work, and thank you for your attention.
So,
Do you have a question? Yes.
So what I don't understand is this doppelganger work.
Yeah.
It's obvious that you said it, that the errors have been put. Why don't you set it like describing by both positive and false negative? So if you have plenty of images, a couple of dropped pairs wouldn't kill you. But as you said, one incorrect link can put two sides on top of each other. So I would expect this to be like said differently.
Oh, yeah. So are you saying like the precision recall trade-off? Like you want,
Oh, I don't like this. Like
okay.
as a user, you usually want something. If I want to use your box, I don't like the
Yeah.
standard setting. And we shouldn't care about, I don't know, there are plenty of pairs that you can connect your scene with.
That's true. I think that's totally fair. And we should, yeah, I think we haven't, kind of properly calibrated this model perfectly. But I think there's another, to me, I think maybe an even bigger kind of win would be, if you classify everything independently, it's like as if you think every edge is independent of every other edge, which clearly there's a lot of correlations. Like there's a group of edges that are very similar to each other and all bad in the same way. So I think, maybe an even better way would be to like find these like structures in the graph.
No, so maybe you did a lot of hard work, and the point is that maybe with a little bit of extra, you can get a lot of more music out of it.
Music, I love that. Yes, I love music.
And besides the fact, no big difference, 86, 95. Now, if you have 99% success rate with somebody 99.99, half the error.
Yeah, good point. Yes.
That's a big deal.
Mm-hmm.
Okay.
Any other questions? Thank you so much. Yoshi.
The chat, but I don't know makes them disadvantage.
Yeah. And next question, please come here and also ask to Mike.
Sorry, I didn't
like
repeat the question. I'm really sorry about that.
Yeah. Yeah. Thank you again.
Thank you very much, everybody. This is really cool. Thank you for having me.
Yes, and video. Yeah.
And perhaps you can put your
Cool.
screen on. This is better.
Yeah,
Yeah, excellent. And share like fully. Yeah, cool.
yeah, I think is it. How do I? Okay, it's good.
It's good.
Yeah, sure.
No. It's good here, but not good on the Zoom. They see both.
Yeah.
Maybe you can put PowerPoint into reading mode as opposed to this presentation mode, which is almost the same, and you will have just one window.
I can do that.
Click on this one. Yeah, this one. Looks almost the same, and now on Zoom it's correct. Because good.
Is that good?
Yes, this is perfect.
Okay. Okay, thanks for the invitation to come to this workshop. Today I'm talking about how to do SLAM inside the human body. I suppose if you know about SLAM, I suppose most of you know about SLAM. So that was made in our lab. So essentially SLAM is taking a set of features, solving a structure for motion, but in real time. And then for every new image, you match features, you locate your camera, you add features to your map for every keyframe, and you are able to recover the trajectory of the camera, I would say, easily, okay? In most situations, okay? This can work building size, no problem, inside a building, outside a building. So what's the next frontier? What about inside the human body? Okay, so what are the difficulties there? Why does SLAM work so well nowadays? Mainly because of the structure from motion that needs essentially to solve data association that comes in several colors, image-to-image data association, map-to-image data association, and place recognition. And all of them are based on the assumption that the world is rigid. Also, most of the time we have a stereo or we have inertial sensor that help a lot to make the system more robust and more accurate. Our view, I'm presenting results from the Endomapper European project, you can see my t-shirt, is to try to transform any endoscope in a smart 3D device. To solve mapping, to solve localization inside the human body, to help navigating the doctors, to be able to perform measurements, to be able to study the coverage of an exploration, to build preoperative models, or to do medical robotics. That's our goal. What's the difficulties? Okay, man-made environments are easy for SLAM nowadays. They were not easy 10, 20 years ago when I started, but now they are easy. You see the first video, you have essentially aesthetic scene, you have good texture, lighting is more or less constant, okay? And look below, the video below. You have a medical image where the scene can be deforming, so ransack gone, okay? Will not work anymore, or almost not work. You have ugly texture, very poor texture, and you have light changes all the time, okay? Because you have an endoscope, the light is attached to the tip of the endoscope, you move, you approach the surface, it's more light. You go farther away, it's darker. All the time you have light changes that are not only global, but also local, okay? So in summary, the main challenges I want to talk about today are deformations of the scene, poor texture, occlusion, dirt, etc. How to address place recognition, what to do with illumination changes, and what about monocular endoscopes? How can we go behind, farther away than using just monocular images? So what's the problem with deformation? Okay, we know in structure from motion, if we have endpoints and M cameras, so if the world is rigid, we have a number of observations that is much higher than the number of unknowns. So we do ransack, remove outliers, everybody works, and everybody's happy. What if the environment is not rigid? The problem is that every point gives two observations, but every point for any state, for any instant, has three unknowns. Gone. Ransack does not work anymore. You cannot reject outliers, so you are trapped. So you need to add some kind of deformation priors or shape priors. So it's a problem that has infinite solutions. So we need to add some kind of regularizers to be able just to find a solution that makes some sense. Okay, so this is a paper that is just accepted, so it will appear in a few weeks on IEEE transactional robotics that addresses this problem, how to do non-rigid SLAM. It's already available on arXiv. So this is an example of a real colon sequence, and this is how our system is able to work in this kind of scenes. Okay, first problem, we have many illumination changes. If you look at the green square, it's the same position, and in two different images, the light is very different, okay? So if you want to use, for photometric tracking, you need to take into account that the light of each feature may change independently of the others. In this case, the main reason here is probably vignetting in the camera. So the camera moved a little, and then, well, you can just add 2 parameters for each feature, just to estimate a gain and a bias for the feature on top of its optical flow. Okay, so this can be done, and with that you can track features reasonably well. But you need to do this composition differently for each feature. Okay, then what about priors? Previous work proposed to use priors in the form of a global mesh in the environment. Global meshes tend to have a planar topology, and they assume that the surfaces are continuous. And that's not really true in many medical images. You see in the right part is an image of a colonoscopy, a real human colonoscopy, and then the environment is not flat, the topology is not planar, and the surface is not continuous. You have some holes, some parts that are not being observed in the image. So for that, we propose to use a representation using just feature points plus a graph that represents which things move together. So the idea here is that close points should default together unless they don't. Okay? So you do a previous hypothesis, you have an image, then you build a graph joining the features you have in your image, and you start tracking these features. Then in this graph, we just decided to remove edges that went stretching too much. So essentially, if the elongation is more than 100% bigger than the first distance, we just cut this edge. Okay? And second, mathematically, we represent the deformation as what we call a viscoelastic model. It means with an elastical term, like in a spring. Okay, these are the equations of the spring in the left part, plus a viscous regularizer that is like a damper. Okay? So to perform deformable tracking, you have the standard data term that represents the reprojection error, and the second term that represents the regularizer introduced by our viscoelastic deformation model that has 2 terms, the elastic one and the viscous one. Okay? So the idea is to estimate the pose of the cameras and the deformations of every point in its time step, in its time stamp, minimizing this error that accumulates the reprojection error plus the deformation regularizer. And this is the result. This is an example with a lever with 2 parts, and you can see here that we are able to track the motion of the camera and also the deformation of the environment. Here in the right part, you can see how the environment deformed, in this case, one part of the lever with respect to the other. The nice part of this dynamic deformation graph is that even though we started with a whole graph, then we were able to cut the parts that were not really tied together. That was for tracking. Then we need to do mapping. To do mapping, we can do the same thing, kind of a bundle adjustment, but adding a regularizer term, that is the term that comes from the deformation. Of course, the Hessian of the bundle adjustment becomes more populated because you have many terms relating each point with his neighbors. Okay, these are the green parts that are the viscous regularizer, and the elastic regularizer are these orange parts. Okay, so the point-to-point matrix is not diagonal anymore. So the problem is a little more complex, that bundle adjustment, but still doable. This is an example with a simulated sequence. a colonoscopy, a simulated colonoscopy. So you can see how we were able to estimate the trajectory of the endoscope and at the same time, the small deformations of the environment. And this is a true colonoscopy with a real person, okay? And more or less, we are still able to track, to build a map and perform tracking and mapping in this kind of environments. Here, the color in the graph represent how much each part of the scene has been deformed. Red means no deformation, while the yellow and green means bigger deformations. Okay, that was about deformations. When we started this project, we thought that deformation was our worst enemy. And then we found out, well, at least in colonoscopies, deformations are not too bad, because I don't know if you know, when they do a colonoscopy, they inflate everything with CO2. And then once it's inflated, it stays more or less in the same size, okay? Once it's inflated. So our worst enemy is not deformation. Our worst enemy is occlusions, water, dirt. I mean, if you do a SLAM in this room, you never hit the walls. If you do a SLAM inside a colon, you always hit the walls. Always, all the time, okay? So it's almost impossible to build a map of the whole colon. You have the SLAM system working for 1 second, 2 seconds, 3 seconds, that's it. And then map, your tracking is lost. What do? Start again the operation? No, you just build a map of 3 seconds, stop this map and start a new one, okay? So to be able to address this problem, you need a multi-map SLAM system. But we already have one. It's called SLAM 3, right? Okay, so it's easy. Let's go. Let's try to do that. Well, the truth is that orb features are not that nice inside the human body. It's very easy to lose the track of orb features. But miraculously, the good old-fashioned sheath features work much better inside the colon or inside the human body. So we took this SLAM 3, replaced orb with sheath features with a GPU implementation to make it faster, and it works reasonably good. We have to tune a lot of things, of course. If you have done some SLAM, you know that for any application, you need to tune up a lot of things, that's true. But well, at the end, in a simulated colonoscopy, in the image you can see on the right, I mean, in an easy one, we were able to do a map of the whole colon, say in only 11 different maps, okay? With a coverage of 93% of the images. That means that 7% of the images were crap because the camera was hitting the wall. What about a real colonoscopy? Well, this is our system working in the cecum area. So that's the end of the colon or the start, depending on which side you are looking from, okay? And then, as you can see, we can build small maps. Sometimes we are able to merge several maps together, okay? And at the end, we get, in this case, a coverage of 38% of the images. So 38% of the images were used for our map. The rest were crap. And we were able to build a map consisting in this case, kind of 96 submaps, okay? Only 96 submaps in a whole column, okay? Okay, then what can we do with a map like that? 96 parts that are not connected between them because there was not enough matches between each part to be able to put them together. Okay, let's move to the next problem. Place recognition. Suppose I want to be able to solve the localization problem inside the colon. You may say, what for? Okay, a practical use is, for example, the doctor does an exploration to try to find cancer in the colon, and then he finds a polyp. Okay, he finds a polyp and he was about to remove it. Okay, wait. Are you sure the patient did not take any anticoagulant? And the anesthetist said, no, he's still taking coagulants. You cannot remove the polyp today. Okay? Okay, so we will not remove the polyp today. We need to do a second operation in 2 weeks to be able to remove this polyp that now we are seeing. Will we be able to see this polyp in 2 weeks? Maybe yes, or maybe not. That's the problem. So that's why you need place recognition inside the colon. You want to come 2 weeks later to the same patient and to be able to tell, go 3 millimeters or go a little further, and here must be your polyp. Okay? So for that, in reality, you only need a topological map or a metric topological map. If we are able to build a topological map of the colon, it's enough to say, go further or go backwards to find a certain place you saw 2 weeks ago. Okay? So for that, just at last ICRA this year, we presented Colon Mapper. That is a system that builds a topological map and is able to use this map to localize the camera inside the map. How it works. It takes every image, uses a convolutional network to obtain a global descriptor, and then we can use this global descriptor to know if 2 places are similar, are the same, or not. Typically, this is not enough. So in this case, just by comparing the descriptors, you can get high score or low score for some images. Just to be more sure that they belong to the same place, we do a secondary test, extracting in this case features using LoFTR and trying to find matches. And if we find enough matches, then we know for sure that it's the same place. Okay, so we use that during map building. So we add images to a first place while we are able to match the images. It's the same place. When we find new images that don't match, we start a new place. Okay, and then we will see here a summary of our topological map. In this case, the topology is simply linear. Okay, it can get a little more complicated. This is an example of verification of whether 2 images belong to the same place or not. And this is our final map. Okay, you can see funny things here. For example, some images are blue. This is because at some moments the doctors use a narrow band imaging that is used to get more strength to the veins and also to do some polyps in the image to be able to visualize them better. Okay, so our map in this case is just this sequence of places. Okay, so 2 weeks later, this was a real patient that was this coagulation problem. Then 2 weeks later, we have a second exploration. And for that, we use Bayesian localization, the good old-fashioned Bayesian localization, just matching features using the descriptor obtained, matching images using the descriptor obtained by the neural network, trying to compute which is the approximate location of every image inside our map, that is this sequence of places. Okay? Okay, so the idea is to be able to use that on assisted navigation. So suppose we want to reach a place that we want to revisit, and then if our localization says we are in this place, in the blue place, it will say go forward, too much, go backwards, arrive. That's the idea, to be able to provide assisted navigation. We are still not there, but we are quite close. Okay, what about illumination changes? As you can see in this image, things that are close to the camera, in this case, are almost burned up, and things that are far away are very dark. When you move a little the camera, the lighting changes totally. You will say, wow, that's a nightmare. That's very complicated for computer vision. Okay, but think twice. Here, darker means farther. So we have 3D information. Wonderful. We have a monocular camera that is given 3D information just because it has attached a light in the camera. Let's try to exploit that. So for that, we need a model. Well, the illumination model says that the illumination goes down with the distance to the square. Okay, so it's the inverse of the distance squared. Okay, so to be able to take profit from that, you need to calibrate your endoscopes, to do photometric calibration of your endoscopes, and then you need to know the radiance of the LED, of the LID emitting the light, the spread function of the light. You need to know the vignetting of the camera. You need to know the gamma that was applied to your video. And then you have the cosine, the typical cosine term of the reflectivity, etc. But if you are able to calibrate your endoscope and to build this illumination model, you can use it to retrieve 3D. Okay, so the idea here is we have an image and we have proposed a neural network that is able to obtain the albedo of the surface, the depth, and from this depth, we compute also the normals, okay? If we have albedo, depth, and normals, we can do rendering, take it into account that that things that are farther away should be darker in the rendering. So we do this kind of rendering, and then we synthesize an image, and we can compare this image with the original one, with the true one. So you get self-supervision of depth for free. No multiple images needed. No, just the light in your endoscopes provide self-supervision for depth. Here you see this boring table, okay? In the yellow part, you have supervised methods that were trained with the ground truth depth, and we were able to match the accuracy of methods that were trained with ground truth depth. The red box are methods that are trained with multi-view, for example, the well-known monodepth technique. Our method is much better than that. Why? Why is much better than monodepth, for example? Because to solve monodepth, you need to register and obtain the relative pose of the two images, and that inside the human body is not easy. Okay, it's quite complicated. While in our case, the illumination is giving that self-supervision signal for free. Okay. This is an example. This works in colonoscopy. This works in gastroscopy. So you can see here live reconstruction for every single image in real time. Once the network is trained, you can throw the network images, and it will give you the 3D reconstruction up to scale. Okay? Up to scale, mainly because we don't know the absolute gain of the endoscope, of the light of the endoscope. Okay. For example, this can be used to measure the size of a polyp. Here you have in a colonoscopy a polyp, and this is the 3D reconstruction. And as I said, our reconstruction is up to scale, so we did a trick. It's just insert a tool here. We know the size of the tool, then we can recover the global scale of everything. So this reconstruction in the right now is with the correct scale thanks to this small trick. Okay. This is another example. You can see the 3D shape of the polyp. So you can measure the size. That is very interesting for doctors, because if it's bigger than 10 millimeters, then the following of the patient is different than if it was less than 10 millimeters. But you can also measure volume or area, whatever. Of course, this can also be used for robot navigation. If you, from one image, you can obtain just the 3D, this can be used to reconstruct the 3D of our environment, and this could be used in future for automatic surgery. Okay, that was 3D reconstruction just from a single image. What if we want to do reconstruction from a set of images? Okay, so one technique that is now very popular is neural reconstruction, either nerve, or in this case, we are using neus. Okay, so here we have, this is a phantom, a silicon colon. Okay, that's why it's easier. There is no water, no dirt, no nothing. Okay, and this is a neural reconstruction we were able to obtain out of it. How to do that? Well, if you just take nerves or neus and try to do that out of the box, this doesn't work. Why? Because the assumption when you use nerve is that the illumination is constant while you take your pictures, okay? And this is not true inside the human body. We know that darker means farther. We know that things gets darker with the square of the distance from the camera and the point of light, okay? So also a nice thing for this application for colonoscopy is that if you do your reconstruction, if you use a technique that builds a sign distance function, a sign distance function represents a watertight surface. Okay, where the value of the function is 0 is the surface, negative is typically inside, and positive is typically outside, in this case of the colon. Okay, so a signet distance function is a particularly good representation for this kind of application. So what we did is building on neus, neural implicit surfaces. Neus, for the ones of you that don't know, is a deep neural network that is able to regress a sign distance function to perform, with this sign distance function, to perform volumetric rendering. Okay, so the representation is an implicit 3D surface. Okay, what happens if you do that without taking into account this term? Essentially, it doesn't work. We will see results in a moment. So what we did is taking the same architecture and just replacing the volumetric rendering, just taking into account this simple equation, that things that are farther away should be darker. Okay, so you put this into the software of neus, you get like neus, our version that was published on MICAI last year, and all of a sudden everything works. Okay. Of course, you need to put into that the endoscope photometric modeling, so the calibration we did for every endoscope. And then you can see here, this is a part of the cecum, the end of the colon. You can see here the reconstruction. If you don't take into account the illumination decline with distance, is essentially crap. Okay? And just by putting this simple equation into the model, you get this reconstruction. much more accurate, and it makes sense. It is watertight. Okay. So the moral here is neural networks are nice, but if you know something, throw it into the model, because they will work much better than if you try to learn absolutely everything from data. Of course, learning from data in medical imaging is not that easy. So we did in this project, in the EndoMapper project, we did a lot of effort. And then we got a data set that we call the EndoMapper data set that has 100 colonoscopies, real colonoscopies from top to bottom, okay? 100 for neural networks right now is nothing if you want to try a sophisticated model, okay? Okay. Okay, this method, like news, obtains some kind of also weird results. It's able to hallucinate areas not observed by the doctor, not seen in any image. Okay, in this case, we have done a small motion of the endoscope from this image to that image. So it's a very small motion, a few centimeters, kind of 10 centimeters or something like that. And then this is the ground truth section of the colon. We know because it's a silicon colon that was just printed. And in the right, we have the 3D reconstruction that our system was able to obtain. The shape is not perfect, that's true. That's mainly because the texture is also very smooth, okay? But then if you project in this reconstruction which parts were seen on some images and which parts were never seen, this is the colors here. Some parts were seen almost 20 times, the blue parts were seen only once, and the gray were never seen, okay? And even though the system is able to estimate a shape that is reasonable, that is watertight. Why? Because we are using a signed distance function. And this has an implicit assumption that the surfaces should be watertight. And you will say, okay, what's the use of hallucinating surfaces? Okay, because we can show the doctor which parts he has not seen. Here we are seeing the colon from the inside, and the red parts were never seen in any image. Okay, so probably the shape is not perfect, it's not correct, but we can tell the doctor here is maybe in this exploration, maybe there is a 20% of the area that you never saw. That's a very important metric to evaluate the performance of doctors when they are doing a colonoscopy, because an area that you have not seen is an area that may have a cancer polyp that will remain there. Okay? So this is what we call coverage analysis. Okay, something wrong. I don't know. Okay. Okay, so I just want to thank my team. Haha, nice. Depending on the view, some of them disappear. Okay. And if you are interested in our work, you can just download the papers. Most of them are on archive or already published. This is my Google Scholar page, and you have them there all the papers. And I'm happy to take any questions you may have. Thank you.
There's a question, thank you. Nice talk. There's a question on the chat. It's asking about FPS of this.
FPS,
Yeah,
okay.
because if there's like a concern if the Hessian is very sparse, maybe it would be slower.
Yeah, FPS. Okay, for the first part, so for the deformation for the non-rigid SLAM system, FPS is around 5 per second, something like that. So yes, currently is not real time, 5-10 per second. It's not like in RGB-SLAM that you go at 30 Hz without much problem. So we are not totally in real time right now. For the other parts I've presented, the one without deformation, the multi-map system, that part is real time at 20 Hz, at 20 images per second, no problem. For the depth reconstruction, let me show it. For this depth reconstruction in the lower left, this is totally real time, a few milliseconds per image. And the light news is several hours to compute this reconstruction. Probably if we use news 2, or if we use Gaussian splatting, we could get much faster reconstructions. But in this paper, we were just using standard news, and the time to train this network to obtain the model was a few hours.
There's one more question about photometric calibration, whether you do it at all and how, if yes.
How to do photometric calibration? Okay, everybody knows how to do calibration. You print a pattern, and you move your camera in a cross around the pattern, and that's it. Okay?
Photometric.
Yeah, photometric calibration is the same thing. Only you buy a Lambertian paper, and you print the pattern in the Lambertian paper. You do the same motion, that's it. Okay? And then you need to choose a model. We use a single point model. So we are modeling, actually, most endoscopes have 3 sources of light, 3 LEDs. We are just modeling like one more or less close to the camera. So the parameters we learn, we calibrate are the position of the light source with respect to the camera, the orientation of the light source, the spread of the light source, mixed with the vignetting, because separating them was very complicated, and that's it. Everything is explained in the papers that you can download from here.
So that covers the Zoom. So I will ask one question. Like all these things, like you didn't say it explicitly, but the fact that you are inside the body means you have full control of the illumination. And this is asking for structured light and photometric stereo.
Yeah, true.
But it's sort of difficult to, you said just a second ago, 3 lights. Technically, if you could switch them in a fast sequence, you could have 3 images.
That's true. That's true, but the problem is that nowadays you have millions of endoscopes around the world in thousands of hospitals, and then you need to change all of them. Okay? Like with that, you can go with that.
Sell it wouldn't mind.
Yeah, of course. Not so sure. They are not so eager to introduce new things in endoscopy, in my experience.
Please repeat the question after, because for the Zoom.
You're in a tube, so is there any way to use the fact that you're in a tube? Do you use a very strong domain frustrator?
Yeah, so the question is, in a colonoscopy, we are inside a tube, and then it is possible to take profit from this prior. Yes, it's true, but we are following more the RGB-SLAM approach. We build a SLAM system that works anywhere. Okay, so if you use priors for the colonoscopy, then maybe you go to gastroscopy and it doesn't work anymore. Or maybe you go to bronchoscopy and then it's a little different. Okay, so we try to prefer to solve it in the most general way we could, just to be able to widen the application field. Yeah.
So for like classic SLAM systems of like UAV or robotics, you might be able to use your accelerometer or your gyroscope or these other sensors to help out with SLAM. Is there anything unique to like an endoscope other than the relays maybe that helps out with rotation? Like, I assume you can get like rotation maybe off of the device itself.
Okay, could you just repeat it?
Yeah, the question is in robotics you can use inertial sensors or other type of sensors. And what about medical devices in endoscopes? It could be, I mean, using inertial sensors will be interesting. I'm not convinced that the type of motions you perform will be that nice for using an IMU. Also, hitting the walls maybe will distract the IMU, measuring forces, but we have never tried because in reality there is no endoscopes with IMU, and we are not good at building things, at doing hardware.
Yeah, it was use the time. Thank you again.
Okay, thanks a lot.
So that's our last
Mario,
talk.
good to see you.
Centroid. First thing, okay. So you need to put your wait. So there is it's the output of your yeah. You feel there. Okay. No, it's not. Is it better? Yeah. Okay. Sorry.
Yours is muted as well.
I am not muted. Okay, now.
Can you hear me now? All right, let's go. So, back from the beginning, I'm very glad to be here to be able to present DUSt3R and I took the opportunity because it's the image matching workshop to also talk about MaST3R, which is very mysterious. And I'll start with DUSt3R and we'll see where it goes. So DUSt3R is joint work with Wang from the Aalto University and colleagues from Naval Labs Europe, and it stands for Dense and Constrained Serial 3D Reconstruction. And the dream we had when we started DUSt3R was really to have a single neural network that would be fed an input image collection and that would output a dense 3D reconstruction. And the unconstrained means we don't have any prior information about the camera poses nor their calibration parameters. And this is very departing from the traditional MDS setup where you consider cameras as inputs. But in the wild, if you want to do photogrammetry, the first thing you need is to estimate the camera parameters. So let's say you start with Colmap, your favorite camera parameter estimation. Basically, the pipeline from Colmap, it always struck me as paradoxical and a bit frustrating because first you extract the correspondences, and from those correspondences, you incrementally build a sparse representation of your scene along with the camera parameters with the bundle adjustment. And it was a bit frustrating because it really means that you need to obtain a 3D scene to get the camera parameters in order to get a 3D scene. So basically, you're solving the problem in order to solve the problem. And this is very frustrating. And it's even more than this, because if you look into correspondences, I can argue that it's inherently a 3D task. So a correspondence, you can define it, or I can define it as finding two pixels that observe the same 3D point. And it really means, it's not because you're not explicitly telling the coordinates of this 3D point, doesn't mean that it's not a 3D task, and I'm pretty sure it is. So the question we had with DUSt3R is, how could we unify all those steps in a single entity that would solve everything at the same time? Because when you look at correspondences, really they are 2D coordinates that observe the same 3D point. But when you look at pose estimation, the camera parameters define a mapping between pixel coordinates in 2D to rays in the 3D world. And it's the same for MVS, actually. You can define MVS in many ways, but let's look at depth maps. A depth map is really a mapping between a 2D coordinate and a depth value, which is exactly corresponding to a 3D point if you know the camera parameters. So in all these sub-problems, you realize that there is a common denominator, which is there's always a notion of mapping between 2D coordinates and 3D space. So really the philosophy of DUSt3R is, what if we just predict this mapping? So what the representation that we chose for such mapping, it's the point map. So the point map, in a nutshell, it's really like an image. So it's a 2D grid of 3D values. But instead of storing RGB values, you store X, Y, Z coordinates. So really, a point map, it's strictly equivalent to a point cloud, but you still retain the 2D information. So you know which pixel goes in 3D space. And this is, we found it very interesting because if you have a network that processes point maps, the network can learn priors on the geometry of the scene, like if you have a planar surface or right angles. But it also can reason on pixel consistency. If you have neighboring pixels in the image that share the same appearance, they're most likely to be in the same region in 3D. And lastly, the point map encodes this mapping, as I was saying. And this mapping is critical because from it, you can extract the camera parameters. You can extract intrinsics, and you can extract rotation and translation. I'm not going to detail too much that, but it's super easy. So this is what we do. The question now is, how do we predict such point maps? So we really like to play around with VIT architecture. So let's put ourselves in the simplest multi-view setup, which is 2 views. We have a VIT encoder that processes each view in a Siamese manner. And then we have a set of decoders. So I separated the decoders here because they're not doing exactly the same thing. I'm going to explain later. But first, just to mention the decoders, they perform self-attention on the tokens of an image and cross-attention between the images, very much like super glue style of image matching. So the first decoder is predicting the point map of camera 1 in red in the reference frame of camera 1, which means the red camera is centered and looking in the Z direction. And the second decoder this time is predicting the blue point maps, which are the point map of camera 2, but in the coordinate frame of camera 1. So this means that both point maps live in the same 3D space. So this is a dense representation of the observed points of the surface. But camera 2 can live anywhere. It doesn't have to be at the origin. It can be really, depending on the training data, everywhere. So I'm talking about training data. We are in a supervised training setting. So we have the ground truth point maps, and we very simply minimize a regression loss that we normalize for scaling values. But that's it. That's just it. It's super simple. We really like this idea because there is no hacky trick for now. So if you look into this approach, you see that we never explicitly told that these were pinhole camera models. Actually, we train with pinhole camera models, but it's never enforced. But we can verify that the predictions respect the training camera model. So the prediction actually respects the pinhole camera model in our case, and we can extract intrinsic information from that. In a perfect world, you could also train this on orthographic camera models or fisheye or 360 cameras even. As long as you have supervision, I don't see why it should not work. This is only speculation. So now we have a network that takes a pair of images as input and is able to output a dense reconstruction in the form of a pair of point maps from which we can extract the camera parameters. And this is, basically this was our dream. We have a network that is jointly doing reconstruction and camera pose estimation. An interesting thing is we started playing around, and the question we had was, what happens if you have only a single image as input? Well, DUSt3R is a binocular network, so you can just feed it twice, and you end up with a monocular 3D reconstruction. And this was significant for us because in my imagination, at least, there was always this idea of orthogonality between monocular 3D reconstruction and multi-view reconstruction. And monocular 3D reconstruction was heavily data-driven, learning priors from data, while MVS was really relying on the parameters of the cameras that you had as input. And you use them for triangulation, use them to search along epipolar lines for the correct depth information. And so, in my opinion, this is a very nice unifying formulation of monocular and multi-view 3D reconstruction. So we started playing around a bit more, and we tried, I'm pretty sure you've already seen that, but I'm gonna show that anyway, because I love it. These are two pictures of Jérôme's office, and as you can see, you can, as a human, infer where the cameras were and what is the 3D scene. But if you look in details, you don't have any corresponding points. You can't establish pixel correspondences because there is no 3D point in common between the two images. And this is the result that we got with DUSt3R. So here for us, it was really crazy because now we can have a dense reconstruction with the camera parameters in cases where I could never imagine doing that with pixel matching, and still can't. So that was very exciting for us. I literally couldn't sleep for a month because of that. So yeah, it was really nice. So let's cool down the excitement. DUSt3R has limitations. We found a couple of them. The two main limitations are that it is a data-driven regression. So a data-driven means if you have test images that are not present, not represented in your training data, then you have no guarantee on the prediction. And as you can see here, there is a human standing, also he's moving, and we don't have any human data in our training set. So the predictions are not great and also not consistent between views. So just to mention here, you see we have 4 images as input. When we have more than 2 images, we do what we call the global alignment. I'm not gonna detail it much here because I don't think it's really exciting. But we have a method to align all the point maps in the same reference system, coordinate system. So the other point is DUSt3R is regression based. And regression is known to predict the average of the possible outcomes according to your input, which is known to be inaccurate, especially compared to classification losses that you could use. And so you can really see on the NVS evaluation that we did on the DTU, we don't have access to the camera parameters for our predictions, but you can see the overall chamfer distance in millimeters is at 1.7, which is nice in absolute value. It's a nice reconstruction, but compared to state of the art, it's really a poor performance. Interestingly, we found that you can extract correspondences from the predicted point maps. Literally, you can find the nearest neighbors in 3D space, and this gives you matches. And from those matches, we do visual localization. For example, we realized that using 2D matching was much more accurate than using the regression output directly. And the problem we had is that DUSt3R was never trained explicitly for matching. And so I'm pretty sure you know where this is going. This is why we did Master. So Master, again, it's as simple as we could make it. It's a work that we did with Johan and Jerome at Naval Labs. And it's the main philosophy is simply to equip DUSt3R with the ability to perform pixel matching. So let's summarize a bit the pipeline from DUSt3R. The three main novelties of Master are that now the point map predictions are done in metric scale. Actually, we realized the normalization was not needed when you had metric information in the ground truth. So why not just predict metric scale through point maps? Okay, this is a small novelty, but the biggest one is really that now we have an additional head that predicts local feature maps. And these are the same resolution as the images, but slightly higher dimensional. And those local features are especially designed for pixel correspondences, and we train them with an info and CE loss, which is basically minimizing the distance between corresponding features and maximizing the distance between non-corresponding features in feature space. And this is a contrastive loss that is much more robust and much more accurate for establishing correspondences. The last contribution we have, I'm not going to talk much about it, but it's very compute intensive to perform dense matching between local feature maps in high dimension. So we have a fast nearest neighbor algorithm that we use because why not make it much faster? Also, it's improving the performance. Okay, so in terms of training, we are still in a supervised setting, and we have overall 14 data sets. 50% are real and 50% are synthetic, and 10 have metric ground truth. So for the other ones, when we compute the loss, we just use the previous normalization, which makes Master as metric as possible. So we initialize from a pre-trained DUSt3R, which is itself was initialized on FOCO. This is a previous work that we did for pre-training binocular BIT architectures for geometric tasks. So, oh, it's not showing. Oh, too bad. We perform many experiments. These are experiments from the archive that we made publicly available today. I'm going to look into map-free localization and multiview reconstruction. You can look in the paper for more evaluations. Okay, so starting with map-free. Map-free is kind of a novel benchmark where the task is to predict relative transformation between pairs of images. But the trick is the translation has to be metric. And this means pixel matching alone cannot do that because you have the scale ambiguity in the relative transformation. And you need to have a way to estimate the scale, which is kind of convenient because now Master predicts metric point maps. Oh, how lucky. And so it's working really well. So what we do is we estimate the scale with Master and we use the correspondences for relative pose estimation. You have many ways of doing that. What we are looking at here are the results of 4 methods on the map-free benchmark. The left image is a reference image that is clicked, and the right images are the sequence that you have to localize. So these are the green trajectory of cameras that you see on the right, and the reference one is the black one at the bottom. So the prediction is the blue camera, and when it gets close to the ground truth, we mark it as a blue dot. So the more blue, the better. The bottom rows are the error in rotation and translation. And as you can see, when the viewpoints get closer, superglue and LoFTR get reasonable performance, but otherwise they are completely lost. And for Master, the robustness to large viewpoint changes is really showing. And it's really showing in terms of quantitative evaluation on the publicly available benchmark, the public benchmark. And when we submitted it, we
improve the performance by a significant margin. I'm not saying this lightly because the margin is significantly significant. Yeah, we were really thrilled about that. And there's no dirty trick. It's really, we predict metric point maps. We have correspondences and we extract the essential matrices and use the point map for scale. Also, they provide training data, which is also helping. So let's look into multi-view stereo 3D reconstruction because I was showing very poor results from DUSt3R before, and now I'm gonna show less poor results with Master. So these are the qualitative reconstructions that we can get. Just to mention that the architecture is not task specific, so we very simply triangulate correspondences in 3D using the ground truth camera poses. And quantitatively speaking, we go down from 1.7 millimeters in chamfer distance to 0.37 millimeters, which is very good and very competitive with state-of-the-art, especially considering that we do not train on the DTU dataset. So for me, it really shows the generalization capabilities of Master, but more importantly, it shows that matching is still far superior to regression in terms of quantitative evaluations. So let's talk a bit about the image matching challenge now. We tried our best. It's hard, it's really hard. So these are results from the lizard sequence. I'm gonna show them again. I'm not gonna detail too much how we obtain them, but just know that we do not use ColMap for that. We have a new global alignment. Oh, I need to optimize the sharing, no? To have nice videos. Okay, sorry online people. Sorry, audience. So we have a global alignment that works with, in this case, 49 cameras. So we make it scale to larger image collections because the previous one was having a lot of troubles with the memory usage because of many things. So in the end, we have a mean average accuracy of 82.25 on the lizard sequence, which for us was really good and better than what we could get with ColMap. But the problem is we don't really know why, but the performance on other sequences were a bit disappointing, and especially on the test set. And we have basically no clue because we don't have access to the test set. Just to mention the church sequence, the symmetry ambiguities are still a pain. You see for those two images, the second image is the black cone inside the church. And so as a human, you can clearly see that this camera is not well localized because it's literally inside the church. But for a matching algorithm, we process all pairs separately. It doesn't make any difference. So there's probably something to be done in the global aggregation of all pairwise predictions if you don't have a holistic pipeline. So in the end, for this sequence, we got roughly 25% of mean average accuracy, but on the test sets, it was very disappointing. And yeah, symmetries, we can't handle them for now. That's it for my presentation. We have code available for both DUSt3R and hopefully soon Master. It's not yet available, but it will be. You can play around with the demos. Many people already did, and we are very thrilled about that. The more you play with it, the better we know the limitations and the weaknesses so that we can improve it. In the end, just to summarize, Master is the new generation that is improving DUSt3R. It's able to estimate focal length, both in monocular and multi-view setups. It's able to estimate metric camera poses, well, as metric as possible, if we can. And we have metric geometry for large image collections, which is also known as mapping, which we could not really do with DUSt3R. And also we get the correspondences, which are extremely accurate in our experiments, except when you have long-term changes, because we don't have a lot of training data with long-term changes. And hopefully this will change with the proper license, please. Yeah, thanks for your attention, and I can answer questions now.
I have actually like two questions, and first is like speaking about like symmetries and this stuff. Like, do you think it's enough if we have like big data, like as Noah was presenting, these like doppelgangers, or like you need something else, like modify the training pipeline somehow?
So that's a tricky question because sometimes symmetries. So when the scene is changing, you have part of the pixels that will not correspond, but when you have symmetries, you will have pixels that do not correspond. And in some cases, you want the pair to be consistently matched, and in other cases, you want the pairs to be rejected because if you use it for your global optimization, it will destroy everything. And this is a very tricky question if you have a pairwise network. So ideally, it would be good to have a lot of supervision from the training data, but importantly, it would be better to have a holistic approach that would take all images at the same time and that would output the whole reconstruction. And if it is data-driven, it might be able to learn prior from the training data. So the problem of having all the images as input is that for now we have a vanilla attention, which is quadratic in terms of the number of tokens, complexity. And so we can't really train that. Also, you might have different sequence length. So how do we train a network with sometimes one image or sometimes 1,000 images? These are questions that need to be answered. We are only 3, so we don't have time to test many things. We try to do our best, and hopefully you guys can also help. We are releasing the training data for DUSt3R now, so we should be able to reproduce our results overall.
Thanks. And yeah.
I have a question about the data and represent simulation. So I think DUSt3R is still doing like 2D basically.
Yep.
So even though you use a lot of data, I don't know so do you think it is possible to scale up further on raw data like unifying focal?
Yeah, that's at first we wanted to use. So the question was, is it possible to scale the annotation pipeline to have a very large network train on very large image collection? And we are thinking about including self-supervised training. Let's say you have image pairs, but you don't have the 3D or you don't have the correspondences, and you could still learn something relevant. We are thinking about that, but it's really non-trivial, and you probably need to mix supervision and self-supervision, because we had experiments with self-supervision where the output was just not consistent with what we knew was the real scene. But this is for sure to be explored, probably in a rendering pipeline way. If you render views from the geometry that you predicted, you could probably do some self-supervised training, but this remains to be answered. And just to mention, creating pairs of images of the same scene is already a rather strong supervision signal. It's hard to build pairs. So it's depends on what you call self-supervised. Thanks. Yep.
Able to get related functions. There's something that is like different from other people. What is the thing that is like?
Yeah.
Please repeat question. Will you please repeat question, for example?
So the question was, how is DUSt3R able to solve this problem, right? So to solve the impossible matching case, well, it's a data-driven approach, so we don't really have control on what's going on inside. But my intuition is that DUSt3R has a very strong prior for monocular 3D reconstruction, and then it has also a prior to align the floors, because the floor are usually planar, and then to align the walls and to create right angles, because we like to live in cubic places globally. And my intuition is that the network learned the prior to align those such that it corresponds to the distribution of the training data. So if you train with square roofs with flat walls, it will probably align the corners and align the planes. And you have, I don't remember the name, but you have other methods that do that in a handcrafted way. They detect planes, they match planes, and they align them such that you can also have this kind of reconstruction. I know it's used for real estate reconstruction when you have few views to reconstruct the inside of the building. I don't remember the name, sorry.
So if you have multiple similar cases,
So if I understand the question,
Yeah, also repeat.
yeah. The question is, how do you handle repetitive appearances, or like if you have two floors of a building that look very much similar, it's just the floor number that changes. How could DUSt3R handle this? And again, if you have sufficient training data, you could try to train it, but this kind of reasoning really relies on small details, and this is an extremely challenging task. Like to be able to disambiguate, it's like the church problem. To be able to disambiguate from the front, from the back, you need to see small details. So I didn't show the hardest pair, but some pairs, you only see a very tiny of the image that is discriminative enough to tell you that this is the backside of the church. And those small details are extremely hard to catch. It requires a high level of reasoning. And I'm not sure DUSt3R architecture would solve that, but we don't have the training data, so it's hard to tell.
Yeah, thank you. You can continue.
Yeah, we can discuss
one last
later.
question, please, and we go to coffee break. Yeah.
Okay, we can fight.
No, we have one.
One.
What's the output of the cluster, and cluster is unconstrained 3D space. So we know that in the camera model that should be constrained in some form by people camera. Should be so question is do you think the simple impression is optimal for no.
No, that's the one.
Okay. That's already a hard question, so I'll try to answer quickly. The question was, so we know in the training we have pinhole camera models. So is it better to use a scene coordinate regression or a point map regression in order to model a pinhole camera model when we know that the 3D points will always lie on the rays of the camera? So there are two answers to that. The first one is, okay, I'm trying to think quick. The point map is an overparametrization of the camera model. So it's really a depth map, but it's free from any intrinsic parameter formulation. And so if you think about that, a depth map and an intrinsic value, a single one, is a parameterization for a set of 3D points if the camera is at the center of the coordinate system. But the point map is really adding a lot of parameters. So it's much less constrained. But hopefully during training, your predictions will go closer and closer to the pinhole camera model if you have pinhole training data. The other thing is there is also probably a notion of convergence of your algorithm. It's easier to converge in a less constrained setting than having to find the focal length. It's really a bad parameterization, I think, for a 3D point to have depth map plus focal length, because it's really constraining the cone of rays along which you're supposed to find a 3D point. And in terms of convergence, it might hinder your training algorithm. This is my take. It's like mostly intuition based.
Yeah, thank you. Thank you again.
Thank you very much.
And here we have a little break for like get oxygen to this room, like caffeine in our veins, and we'll be back in 15 minutes with our paper talks, and then one more break, and then challenge talks. Yeah.
Like with the table, like okay, it's like one thing that you can like nothing like it's a little line. Yeah, it depends. No. I think that one core is not English, but there is still one thing you have to need. Now, if you can shift and we don't have the answer for that. Okay, but have you ever been? You know the yeah. So it's the table. That's the table correctly. Yeah, it was. Well, you can try on your own data.
Okay, welcome back. And now we'll have our like paper. Like we were like super selective, so this like really great workshop papers. And it's my pleasure to introduce Johan, who is like, I think in like this and maybe a couple more years, he's like one of the guys in SFM and image matching. So yeah. Oh. Why it didn't work? Yeah.
Hello, hello.
Oh, amazing.
Thank you for the kind introduction. How close do I need to stand to this to make sense? Maybe like this. Okay. Hello, everyone. Nice to see many faces. I'm here to present a paper. The name of the paper is DUSt, and there's a V2 on it, which indicates it has been upgraded. And the rest of the title is kind of homage to Keras, because I like Keras. But yeah, what we did in this paper was to analyze the DUSt detector and see what can we make better, what do we need to change, and make these improvements. This is a joint work, so it's not only me. So you can see I'm Johan. There's also George in the back. And there's also Sunjun, who could not come here, sadly, but he is also on the paper. I appreciate all my co-authors.
You're sending your elbow.
Oh, my elbow.
So
Okay, that's the wrong.
So no, it's okay. Just like you have to tilt the camera.
Oh, okay.
Look at this. Still a little bit more.
Okay.
And now you're fine.
Okay, now it is a face.
All the ladies can appreciate you on the.
Thank you. Okay, great. Now, maybe I even move it a bit here. Okay. So now the online people might be able to see me. Hello. Okay. So I'm going to give a very brief introduction to the DUSt detector. So DUSt detector is a learned feature detector that we made recently. It was presented at 3DV this year. Yeah, it's a key point detector. Basically, what it does is it's kind of trained to detect SIF detection that survive SFM. So basically what we mean by this is someone ran SFM on a data set. Maybe it was megadepth. And we take all the detection that got connected to a 3D track. Basically, these are somehow good detections. They were consistent over views. They made this nice track. We like them. We call this the detection prior because that's kind of what we start with in some way. It's also trained simultaneously to maximize some kind of self-consistency. This was actually the original thought of the project, was to make a detector completely away from a descriptor. The descriptor came way later in this project. But basically just take two views, maximize the consistency. So we have like detection logits. We try to make them consistent between the views. We do this by cross entropy, and we do some top K, whatever. It's not so important, or it is important, but it's not so important maybe in this talk. And then we also regularize it to spread the detections out over the image so that it doesn't get too concentrated on any specific region. Okay, so there's also a question mark there. I don't know why there's this is supposed to be an arrow. So it went from V1 to V2, but now it's V1 question mark V2, but that maybe also makes sense. The question mark will be explained as we go along. So as you can maybe see, maybe you don't see, depending on how far away you are. We have some detections shown in the first model, and we had some detections shown from the second model. And if you look kind of blurrily, they kind of look the same. But then you look closer and you find there are like a bunch of issues with the first detector we made. So one of the issues is like really obvious detections, such as on the top of this building, on the antenna, or I don't know what to call this, the cross. You have things that really should be detected, but it's not detected in the first detector. And this is due to dataset issues and all this type of stuff. I will get into it. And we have the new detector, and it turns out, wow, it's much better. It detects kind of all the points we want it to detect. It's kind of well spread. Great. That's good news. And okay, it doesn't only look good, we actually do some quite major improvements on a bunch of benchmarks. So just compare different stuff. So we compare, basically we keep the descriptor fixed, we only change the detector. So we haven't actually retrained the descriptor here, we just use the good old DDOD descriptor. And yeah, on MegaDepth 1500 and on the IMC 22 benchmark, we get some pretty big improvements. What's quite cool is if you look at the bottom right here, like 78.3 is actually quite a good IMC 22 score. And the cool thing here is we're only using a detector and a descriptor, none of this dense matching or semi-dense matching. Really cool. Okay. Yeah, another cool thing, but maybe not so cool thing if you start thinking about it is, so what's actually different in the new method is one thing we did is we actually started looking at what happens during training. Previously we just kind of looked at, okay, we know we have the nice repeatability objective. We will maximize the repeatability. It turns out the repeatability increases on the test set. It all looks good, but actually when you solve for pose, so if you have pose lib, any type of nice ransack, actually what you see in these curves is the orange curve, which is the like pose area on the curve. It goes down quite soon in the training and the repeatability keeps going up. So what we basically did is we just kind of chopped off the training time. So before we trained for 10 hours, now we train for about 15 minutes on an A100. Sounds really good, but you can already tell there's something a bit sketchy here, right? Okay, other good things. I mean, I would just keep saying some nice things. Like if we compare qualitatively again, maybe to DISC compared to DDOD, we can see some differences as well. Like DISC has this kind of nice property that the detections are kind of well spread out over everywhere, but it doesn't really, it's not really discriminative. It doesn't really converge to any really repeatable points, while the first DDOD, it finds these really repeatable points, but as training goes on, what will happen is it will take only the really, really repeatable key points and ignore large regions of the image, despite us having this regularization and all that. While with the V2 DDOD, we get repeatable and kind of well-distributed key points. You can kind of see that it takes most. It still ignores some regions, so there's still kind of work to be done. Yeah, so also we don't only just cut the training time, because then we wouldn't get accepted maybe. So we also do some other stuff. So we do NMS, so non-max suppression, which is everyone kind of does at inference time. We don't do it at inference time. And actually, we still don't do it at inference time because it still reduces post-AUC. But it's good to do during training time. So we have, I talked very briefly about the top K objective. In this, at this time, we do the we do a non-max on this to ensure that our targets are not, are not clustered basically. And of course, similar things exist in previous work. So if you look at R2D2, they have a peakiness loss there. We also experimented with other types of losses, such as a peakiness loss. Didn't work quite as well. And actually these key point networks, they find really weird solutions to minimize these type of losses. I'm happy to talk more about that later if you want. We also did some minor improvements. So basically we just updated the test time, the train time augmentation. So we did a bunch of rotation augmentations to make sure that the detector is robust to big rotations. This is actually already kind of in the steerers paper, but we integrated it into this framework as well. Also, one thing that you might not know is that the top K objective in the original DDOD, or probably you haven't even read the original DDOD, but there it says the top K is done per image, but actually it was done per batch. If you look at the code, now we do it per image, I promise. And this is good. This is good. And yeah, the thing with doing top K of our batch is the original thinking was it can be good because some images basically have less interesting features. So we should kind of have it over a batch. But actually what can happen then is that the network is not very good at certain images. And then we let it kind of ignore those images. And that's not such a good thing if you want to train a good network. Yeah, we also tried a bunch of things. So don't try these if you want to improve it. So don't, I mean, you might be much better at this than I am, but what we tried was basically, maybe we can do some post hoc stuff. Maybe we can modify the logics in some cool way to make stuff better to get this nice spread. Didn't work well. Modifying the detection priors, maybe instead of SIFT, we could use superpoint or something like this. Didn't work well either. Maybe if we do like a bunch of detectors as priors and train that, it could work better, but that's such an ugly solution, I think. Yeah, modifying K, changing the regularizer, changing learning rate. It turns out 10 to the -4 is the best learning rate. Don't change it. Resolution doesn't matter. And yeah, this non-max suppression during inference was also not useful still. And I'm thinking maybe it's not really good for SIFT type detectors. It might be better for corner type detectors, but I don't have much proof for this. Yeah, so there's some bad news, I guess, in this, which I implied from the start, which is basically that this repeatability metric is kind of inherently not the right metric to optimize if you want a good key point detector. What you really want to optimize is the pose area under curve, or something that's actually the downstream thing you want. And there are works in this direction. I mean, there is already differentiable ransack in multiple forms. But I think not many people have gotten it to work well with key point detectors yet. I might be wrong. I've seen some work on like detecting key points in 3D, which uses pose errors, but they are still kind of tricky to work. But I think this is kind of the thing you want to. You need to find an objective that actually aligns with what you want in the end. So that's something I would hope. Yeah, okay, final slide. Yeah, you can find the weights in this GitHub link at the Poshcat DDOD, or you can use Cornea. Yeah, and these are the new weights over here. It's a V2. You just change that line and hopefully it should work. Let me know if there's some bug somewhere here. There might be. I heard one of the IMC teams used it, so I'm happy that it worked out for them. Yeah, if you're gonna get in touch, you can yeah, just get in touch here or at me, or open an issue on GitHub. I have a lot of them. Okay, another final slide. We have also a poster for Roma later, super late on Friday, shitty time. And an oral and a poster for steerers with George. That's on Wednesday, so definitely check those out. Also, one last thing. So, okay, a key point detector detects, okay, that makes sense. The points that it detects are called detections. That makes sense, that makes sense. A key point descriptor describes, yeah, okay. The points that it describes are called descriptions, yeah.
Oh.
Some people accidentally misspell this as descriptors. I don't know how this misspelling got into our literature, but it's actually called descriptions. Okay, I think that's it. No, okay. Yeah, I will be working on matching again this autumn. Looking for more people to collaborate with. If you want to collaborate on something, let me know, and let's do something. Okay, that was the actual.
Thank you. Unfortunately, there is no time for questions. We're super over time. I also want to comment that that's how our workshop started. We said that like repeatability is not a good metric.
Yeah.
Yeah.
Now we've gone full
Yeah.
circle. We're saying
Yeah.
it again.
So, Apple people, yeah, fine. Yeah, I'm here. I have even a keynote here. So you can do this. Yeah, okay.
Hello everyone. Hello everyone. My name is Honghai Chen, and in this session we present fine-based formattation for the semi-dense mesh regime, and this is work done by the joint work done by the Apple and the Hong Kong University of Science and Technology. Okay, so we first do a brief recap of the different meshing paradigm. Maybe a little outdated because it doesn't include the DUSt and Mast3R that is just mentioned. But so let's recap. So we categorize meshing paradigm into three parts. The first is a traditional sparse meshing paradigm, which includes keep on protection and meshing. And then we have the semi-dense regime, which means that we encode the full resolution image into a feature map, and we do some feature augmentation, typically through the cross-view transformer, and then we do the matching and do refinement to get sub-pixel level accuracy. And very recently, we also have a very powerful paradigm, which I think is a refloration of the fully dense regime in the optical flow-like method, that we encode the feature map into a cost volume, and we use a decoder to get a full resolution match output and do sampling. The typical one is like the ROMA and the DKM, which shows very powerful performance. And our work falls into the second, that semi-dense regime. Why we don't do the fully dense? Because we find that if we want to obtain a very good result in the fully dense regime, we need have a backbone and decoder and many parameters in the network. But we also want to, so we want a lightweight network, and we also want to benefit from the dense regime so that we don't be restricted on the key point. So we choose the second one, that is a semi-dense one with a relatively lightweight network, and also we don't need to detect key point. So as a very typical method in the semi-dense regime is LoFTR in CVPI 2021. The basic structure is that we extract the feature map from the user CNN, and we conduct a cross and self-attention among the tokenized features. And after that, we do a linear stable matching, and after that, we do the refinement. So we think about the very important part of this paradigm, that is how to we define the transformer or the tension in this cross-view operation. So since that we know that the linear attention has a quadratic complexity and our image has many pixels, so if we want to do a full resolution, it's almost impossible. And to prevent this, there's something like a linear approximation in the original LoFTR paper. And also we can similarly do a resolution reduction by the polling operation. And actually there's a CVPR work in CVPR 2024 about this paradigm, that is just do it in low resolution and achieve good results. But actually this is a global attention. That means we sacrifice some granularity for the efficiency. To achieve a high resolution output, we want some fine granularity interaction. That's what we call global local attention. That means we do globalization at a low resolution feature map. And by some means, like we regress intermediate optic flow through the attention process, we can locate which part of the image correspond to other parts on the opposite image. And we just cast the attention pattern upon the opposite view and sample local attention span. And we do attention between these paired span pairs. So that we call the global local attention. And in ACCV, we present a previous work to adopt this kind of things like the global local attention, and after which we fuse this message from the global and local scale to form the basic operation of an attention framework. And we think in this direction, and we find two things that may hinder the further performance improvement. And one thing is how do we define the local attention span? So our idea is that we want to maximize the overlap ratio between the cells and target attention span. So that means, but that is not very easy in the two-view geometry because we have deformation across views like scaling, shearing, or other translation. So idea is that we can estimate a piecewise deformation field from the intermediate optic flow we predict and use it to shape our attention span. And in this work, we choose a fine field to shape this, to define the deformation field. And another issue is about how do we fuse the global and local attention message. Actually, we know that the local message we obtain can sometimes be unreliable either due to the inaccurate optic flow regression or just because these two image, some part of the image pair doesn't overlap at all. So what we want to do is that we need a reliability score, reliability metric to determine the weight that we put on the local and the global message. So we prevent this work. That is a fine former. It's a deformable attention. It's a semi-dense matching with deformable attention, and also a selective global local message fusion. So we just briefly walk through the pipeline, and actually what matters about how do we design the global local attention in the cross-view message exchange. So the first step, we downsample the input feature map into a relatively low resolution, and we conduct a global attention in this stage. And we know that in global attention, we will have attention matrix that depict how similarity, which part in image one correspond to other part. And we take inspiration from some dense method that use this similarity matrix to weight the positional encoding token on the other image and regress intermediate optic flow. So after the intermediate flow regression, we upsample it to the original resolution and use it to regress our deformation field. So this part is about the flow regression and the global attention stage. We have a hat that is the attention matrix in the global attention stage. And we have the P, which is the position encoding tokens. And we have a convolutional predictor that you predict the optic flow from the weighted position tokens. And we inherit from our previous work that models flow as a Gaussian model that gave us a probability of the estimated flow field, which means we don't only have the flow coordinates, but we also have its uncertainty. So we use it to estimate a deformation field, which means that since we have a piecewise optic flow field, and for each patch, we can feed a local six affine parameters that are affine matrix, and it constitutes our deformation field. And for each source tokens, we use it to deformation field to cast it upon the target views, which forms a deformed attention span. And we just conduct attention between each of the span pairs. So after done the global and local attention, we do a fusion. And as we mentioned that we want to put different weight on different part of the fusion stage. So we just use because that we can also obtain a uncertainty score for each predicted flow. So we use it to design a matrix that put more weights on the more reliable prediction and use it to weight two parts in each location. So after that, we just do the normal operation in the attention, that is to fuse this two stage and pass it to the feed-forward network to obtain our updated features. And also we have a refinement stage, which means we to obtain a sub-pixel level accuracy from our cost matches. And in terms of loss design, we have a cross entropy loss, which is designed for the cost matching and fine matching loss. And one thing we find that is if we apply additional spatial software max loss to upon the assign matrix, we find that it will further improve the matching completeness. And we also conduct the relative post estimation on the two classical data set, the ScanNet and MegaDepth. And we have obtained high result on both the previous semi-dense state-of-the-art work. And we also test the generalization ability of a method. That means we use the model trained on MegaDepth to obtain the pose on ScanNet. And we find that if we compare with LoFTR, the MegaDepth trained model can achieve higher accuracy than the ScanNet trained LoFTR. And we also test about the accuracy on different model size. Since we have a lightweight model that is the third row with only 2.1 million parameters and almost 1/3 of the flows compared with LoFTR, but achieves high results on MegaDepth. And to the production study, we find that if we directly replace the focal loss with the spatial softmax we propose, we find that it will degenerate performance. But when it combined with the focal loss, it will bring a very large performance improvement. And we also validate the different part like the local tension and selective fusions and the fine deformation in our method. So the last part is about some visualization. We can see how the south patches are projected in the target one use a deformation field estimate, which covers both scale change and sharing change. And about the matching results. Thank you. So the code will be released in this link after it's prepared. So any questions?
Thank you. I think we are a bit over time, as same with first talk, so no questions here. Yeah, that's right. So like next speaker, and I would like to ask you to be a bit mindful of schedule. Yeah, and next speaker would tell you how to match from space. Yes.
Thank you. Hello, everyone. So I go like this, right? I'm Gabriele Berton, and I'm going to talk about our paper Earth Match. There's not much technical novelty, but I promise the task is very cool and the insights are interesting as well. So I'm going to start by telling you that astronauts take a lot of photos of Earth. They are up there in the International Space Station. There's a cupola, and they take photos with a literally like DSLR kind of camera. And right now we have over 4 million photos taken in over 60 years. And before going up there, astronauts undergo photography training. So they tell them what they should take photos of and how to take them, because the ISS is moving very fast, so it's not too easy. These photos are used for scientific research, like long-term climate change study and emergency response. So for example, they take photos of wildfires, floods as they happen, and volcano eruptions. So for example, by just turning the camera oblique, they can measure how high the volcano eruption smoke is, and that can help, for example, to divert flight traffic, for example. But these photos do not automatically come with the GPS coordinates with their localization. So these are sent to Houston, to NASA, and there are scientists there that manually localize these photos, manually. And then these localized photos are then sent to the authorities anywhere on Earth. Localization, as you can guess, is a very difficult task because the search space is very large. This is what an astronaut sees from above Earth. The ISS is 400 kilometers above the Earth's surface, and they see an area that is roughly as big as North America. And the search space of the people that need to localize these photos is just as big, and these photos cover as little as 0.0005% of the visible area. And so localizing this photo is as difficult as finding a needle in a haystack. But these are actually very important. So 300,000 of these images have already been manually localized by hand, and not to collect some data set just because they're useful. And so this is, in the words of NASA Earth Observatory, this is a monumentally important but monumentally time-consuming job. Sorry, there was a video of a person actually doing the manual localization here. Okay. So how do we localize these images? At first, we do image retrieval. So we sample a lot of images from Earth. These are photos, basically, we cover the whole Earth. These images are taken from satellite images, like Sentinel-2 type of images. They're open source. We can sample them at different resolution, because when astronauts take photos, we don't know the resolution. We know the camera lens, but we don't know the extent of the covered area. So we sample them at different resolution, different rotations, because astronauts don't know where is north. So all these photos are pointing all different directions. So we rotate them. We create this giant database of 700,000 images, and then we run image retrieval. And with image retrieval, well, we can get a candidate. So as you can see here on the top right, there is the astronaut photo, which is the query that we want to localize. You can see the occlusion there from a part of the ISS, and then we get a prediction, like the most similar image from the database to our query. And I'm not going to go too much into this, but because this is from a paper that I'm going to talk about as a poster session on Thursday morning. So I'm not going to talk about the image retrieval part. I'm going to tell you that these are the results of some qualitative results of image retrieval. You can see on the leftmost image is the query, and there are some predictions. Well, these are correct predictions, so we're happy with this. But this is a different query, and these are wrong predictions. So we're not happy with this, and want to automatically know which are wrong and which are correct. So this is an issue of image retrieval, is that it does not provide confidence. Can I move this? Okay. Okay. Image retrieval does not provide a confidence score, or it does, but it's not unreliable. So we actually do want to obtain a confidence for each prediction. So basically, by post-processing the candidates from the retrieval, we want to get a confidence. We want to obtain a pixel-wise localization. And that's because, for example, if they take a photo of a wildfire, we want to know the extent in terms of latitude and longitude of the wildfire. So like precisely per pixel. And finally, we want to run a fair out-of-distribution image matching benchmark. And I'm going to tell you what that means very soon. Okay, so to get a confidence score and to pixel-wise get a localization of the query images, we do image co-registration. So basically, we take the query, we take the candidate, we pass it through a image matching model, we get a homography, and then we get we can transform the candidate and get an image that looks more similar to the prediction. So as you can see, the colors are very different, but the first image, like the query, is the same location as the image in the end after the transformation. And like this, we get a confidence level because the number of inliers is a good proxy for a confidence. And we also obtain pixel-wise localization. So for each pixel, we know the latitude and longitude thanks to the homography. In practice, the way this works is actually we do an iterative process. So we don't compute the homography once and do the transformation. After we do the transformation, we do it again and again, a few times. And as you can see at the beginning, the two images are very different from each other, but after a few iterations, they start matching perfectly one on top of the other. And then we know that the prediction is actually correct and that we can confidently say that the prediction is correct with high confidence. So, well, I showed you a little bit the pipeline. There's the retrieval, the homography, the image matching. But so we were, now we had the question, which matcher should we choose? Should we train our own? And well, before training our own, we wanted to try previously existing matchers. And we found that surprisingly, they pretty much work very well. Like this is a very much auto distribution kind of task. Most of these methods are trained on buildings, outdoor kind of images, and then we test them on satellite images, and somehow they still work. So we tried 17 different pre-trained matchers, and we ablated a number of things like image resolution and number of key points, which is something that usually we don't see in literature because we only care here about maximizing the results. And I'm just going to show you this one result, which is the one I found the most interesting, just with a subset of the methods that we benchmarked. By changing the image resolution, well, obviously small resolution means better results, but what we did not expect is that with different resolution, the best performing method changes, and it changes very much. You can see here that with 4 different resolutions, there are 4 different best performing methods. And personally, I'm very happy that we did this ablation because otherwise we could have just fixed the resolution to 768, for example. These are square images like 512 by 512 pixels, and would have said that one of these is the state of the art, which would have not told the entire story. And obviously, to run this code with 17 different models, we had to make a repository, to make a code base where you can easily try different models. And so right now we're actually supporting 23 of 23 models, and we just showed 17 in the paper. And these all come very easily to use with a unified API. I hope this is open source. We put it on GitHub. I hope it's going to be helpful for many of you. You can just git clone the repository and just run python main.py and just pass the matcher name. Everything should be running out of the box. So to summarize, we produce confidence level and pixel-wise localization for these astronaut images by post-processing the output of the retrieval. We ran the largest auto-distribution image matching benchmark, and we provide a code base to easily test dozens of matchers. Code and data sets are available, and I hope that the code will help you in any kind of project you might have, and I hope that the data will push you to at least try to work on this highly relevant task. So thank you for your attention.
Now we have time for one question. Who would be this lucky person? Nobody.
Yeah. When you spoke about maximizing the number, like the dependence on the number of key points matched as a function of resolution, the graph was in percentages.
Yes.
So how does number and percentages?
Yeah, okay. So here I only showed so the percentage is the percentage of image that we correctly localize, and on the x-axis I show the image size. In this plot, we don't show the number of key points.
Okay.
There's another plot for that. Yeah.
Yeah. Thank you again.
Thank you.
And additional thanks for making everything open sourced. I love it. And next one. Cross LoFTR or something? LoFTR. Great.
Hello, everyone. My name is Aybora, and I will talk about our work, LoFTR, cross-model feature matching transformer. Well, matching local features across different views is a fundamental problem. And visible thermal image matching is a special but challenging case. It's special because the thermal image is always robust against the adverse light and weather conditions. For example, in this foggy image, you can almost see nothing, but the thermal one is more crisp. But it's also challenging because the texture characteristic and the nonlinearity intensity differences between the RGB and thermal spectra. And thermal cameras typically have lower resolution and field of view. And despite many handcrafted learning-based methods are available, the performance is still suboptimal. As you can see in this image, there are many differences because of the texture characteristics, and in literature, up to now, there is no available image matcher that supports both multimodality and multi-view. So based on the LoFTR algorithm, we have introduced the LoFTR algorithm, and we follow we have three contributions. The first one is we follow the two-stage training approach with pre-training first and then fine-tuning with augmented images. And we leverage the mask image modeling to address the multimodal dataset scarcity. And second one is we follow the fine matching pipeline, which for the pre-training phase. And we enable the one-to-many matching, which we follow the ADA-matcher algorithm in here. And we ensure the reliable texture matching at reduced scale of 1/2. In this imagery, you can see we now available in the one-to-many matching for the 1/8 scale. And our third contribution is we introduce a new dataset, the visible thermal image matching dataset called DUSt3R. And it has various viewpoint differences and weather conditions, such as the cloudy to cloudy or sunny to sunny or another combination. And to gain robustness over differences on intensity, we introduced the mask image modeling based on the p-match algorithm in literature. And for training, we have used some available thermal datasets, which is called as KAIST multispectral pedestrian detection. And we randomly create some masks that cover 50% of the image with 664 to 64 size patches. And we follow the fine tuning, but there is no available thermal data set with depth information. So we have created pseudo-thermal data. We applied the modified version of cosine transform on RGB image. And the crucial part is the gain endurance against nonlinear intensity variations. For this, we directly use the megadepths available data sets, but we have converted them to pseudo-IR. And as you can see, our modified cosine transform algorithm is the simple but effective algorithm. This is original RGB and this is original IR data. And the pseudo-thermal is very look-alike to the thermal imagery. And I think there's something wrong with because of the
What's wrong?
Google slides. There are some, I mean,
It's difficult for Metro to do it in real time. We have to.
Yeah, like, okay, so.
yeah, okay, let me go on like that. We have used the CNN feature extraction backbone, and we get the 1/8, 1/4, and 1/2 size scales of the features. And we have used these 1/8 scales features for the course level matching module. We use two 1/8 scales features to get the one-to-many matches available in the course level matching. And we feed this matches to fine level matching module along with the 1/2, 1/4, and 1/2 level matches. And we use all of these scales in using the concatenation, self-attention, and cross-attention. At the end, we get the 1-to-1, 1/2 scaled matches, and we feed them to subpixel refinement module to get matches over the subpixel level. And here are our results on the relative pose estimation on MegaScenes, cloudy, and cloudy sunny datasets. And please note that there are not many available algorithm in the with the code algorithm in the literature. The only ones are the Redfeed and LoFTR and MTV, and we tried them with RGB-thermal, but the other ones are trained with original RGB data. And our proposed LoFTR algorithm on average increases their performance by around 28 points. And here are some qualitative results, and these are also verifies our findings. As you can see, our LoFTR gives much reliable and less error results. And it also works with different homographies. And these each aligned visible and thermal image pair from these data sets is used to generate 5 different image pair through homographic transformation. And as you can see, even though we change the homography, we still get great results. And this also quantitatively verifies our findings. So to conclude, leveraging the 2-stage training and mask image modeling, LoFTR significantly outperforms the existing methods in visible to thermal image matching benchmarks. And addition of one-to-many matching provides the robustness across different viewpoints and texture diversities, which are the original challenge in the visible to thermal matching. And we achieved the state-of-the-art performance on a newly introduced data set, and we increased the area under curve score around 28 points, which validates the effectiveness of our methods. And for the future work, we are planning collecting large amounts of data consisting of visible and thermal images for training purposes. And we try to obtain the ground truth pose and depth to collect data with LoFTR. And finally, we are planning to utilize the foundation models with high generalization ability. So thank you for listening. The code will be available in a short time. Also, you can access the paper via the link or the QR code. Now, if you have any questions, I can answer them.
For presentation, so I have 2 questions. The first one is, I look at the points that are matched between RGB and thermal images. Do you see any pattern? I mean, are they mostly the object boundaries? Because consider wall, I painted the wall, but the color is always the same. But in the RGB image, you have textures. The thermal image, you don't have textures only on the part. So you just make boundary of the walls. Do you see any patterns like that? And after this,
No, just one, please.
Can this approach be extended to dance matching?
Yeah, actually, as you can see from this image, we lost lots of the texture patterns in the thermal image. So we have to just focus on, for example, the edges or something like that, because it's impossible, I believe, to focus on the paintings or something like that. And for the second question, yeah, I believe it can be adapted to the dance matching, yes.
So our final talk, RGBT, anyone? Okay, so this is, I download this, one moment, yes, so this, wait, right. Yeah, here we go.
Pleasant good afternoon to everyone. I'm Amulya Pendota, and this work has been done under the supervision of Professor Sumohana Chinnapaya at Lab for Video and Image Analysis, IIT Hyderabad, India. And the title of my paper is Are Deep Learning Models Pre-trained on RGB Data Good Enough for RGB-thermal Image Retrieval? So this would be the outline of my presentation. Starting, I would like to introduce with the introduction, the problem statement, RGB image retrieval, the conclusion, and the future scope. So coming to the introduction, so in image retrieval, for a given query, we ideally would like to retrieve a visually similar image from the reference database. And the applications majorly involve place recognition, surveillance, monitoring, autonomous navigation, search and rescue operations. However, the existing methods mainly work with the RGB data alone. But if we wanted to work on all day, all weather scenarios, relying solely on RGB data will not give us trustworthy solutions. And hence, we wanted to look into RGB thermal image retrieval, where the query and the database come from a different domain. So coming to the problem statement, if you see the figure 2, column 1 and column 2 represents RGB and its corresponding thermal imagery, which are taken at low level illumination setting and at adverse weather conditions. So if we see the visual information that we get from RGB image is not so informative here, and we see that corresponding thermal images are giving us better information and helping us understand what exactly the scene is about. So here the objective is to design a reliable RGB thermal image retrieval solution to perform in all day, all weather scenarios, especially when RGB image is not unreliable. And we see that matching multispectral images has been a major interest in the community with a focus on RGB and NIR imagery. However, as the NIR band is very close to the visible spectrum, we see high correlation between the RGB and NIR imagery. Like if you see the shadows here or the design that we see, they are present in NIR imagery as well. And we feel that solving RGB and NIR imagery is much simpler than solving RGB and thermal imagery, which is FIR, like far infrared imagery. And moving forward in the related work, it is mainly classified into 4 different categories, with the first 3 categories mainly focusing on RGB and NIR imagery. And people have focused on different kinds of matching images, they have been trying to match the pairwise images rather than matching images in an image retrieval setup. So the first category comes under classical key point based techniques, where they try to focus on gradient based techniques, edges and all. And the second category comes as learning based key point techniques, where they try to use the deep learning methods and try to extract feature descriptions. And the third based technique is a image patch matching similarity, where they try to match the given patch instead of a high resolution image. And the fourth category is a visual place recognition methods, which try to employ image retrieval techniques. And majorly the state-of-the-art VPR methods have had datasets which have geotagged information, and all the models are trained on datasets with geotagged information. So the ideal setup here, we would like to train a VPR model for RGB thermal image retrieval task on RGB thermal datasets. However, the lack of RGB thermal image retrieval task-specific datasets, that is missing of geolocation information with the existing datasets, is stopping us from training the models, training the VPR-like models. And so this made us look for alternative datasets which are existing and are called as a benchmark datasets for fusion-based object tracking or fusion-based object detection. So all these datasets we have used for evaluation, and these datasets doesn't possess geolocation information, except the boson dataset here, which is used for thermal localization application. But however, this boson dataset was taken in a desert sort of area instead of city kind of setup. So, these challenges has stopped us from trying to train VPR-like models on the available RGB datasets, and hence we wanted to see the suitability of the existing pre-trained models which are trained on RGB datasets for different tasks for RGB thermal image retrieval task. And so this is a overview of the pipeline. Given a RGB image as a query image and a thermal imagery as a reference database, we pass them through a pre-trained model, which is trained on RGB data for different specific tasks. And we try to gather the feature descriptions and then try to get a best retrieval image based on the least distance. And we say the best retrieved image by the model is a correct match only when the index of the best retrieved image is exactly same as a query index. And moving forward, these are the pre-trained models that we have considered to evaluate the suitability for RGB and thermal image retrieval task. And these are the main contributions of our paper, an extensive evaluation of the pre-trained models, a demonstration of why the pre-trained models are doing better than the state-of-the-art VPR techniques, and an explanation of the factors contributing to the superior performance through different qualitative and quantitative evaluation techniques. So starting with the quantitative evaluation, we use recall at 1 and recall at 5 to evaluate the efficacy of a pre-trained model over RGB thermal image retrieval task. And if we see here, these are all ImageNet pre-trained models trained for classification tasks. And these are the VPR methods, state-of-the-art VPR methods, which are trained for place recognition tasks. And these are the multimodal methods, which are trained for different tasks like classification, object detection, etc. On multimodal data. And SGM is a baseline, we treat it as a baseline model, which was trained for thermal geolocalization tasks on boson dataset, which is basically a desert kind of dataset. And if we see the results here, the bold represents the higher recall rates and the underline represents the second best recall rates. And we have observed that SqueezeNet, ImageNet pre-trained model, is consistently giving us higher recall rates over all the datasets except the boson dataset. And on boson dataset, we have seen that the baseline model is giving us the highest recall rate as it was trained on that. And we also see that despite being trained on RGB and thermal imagery, the baseline model is failing to generalize over all other datasets because of the nature of the dataset it was trained on. And we have also seen that the state-of-the-art VPR methods are also not doing great here. One reason could be that VPR mainly focuses on background aspects of an image rather than the foreground aspects. And we have seen that the datasets that we have used for evaluation has more of foreground changes rather than background. And we also have seen that the image pre-trained models are doing relatively better than the other pre-trained models. One reason could be the commonality that is present in the classes that are present in the foreground of the evaluation dataset that we have used and the ImageNet dataset. And we also see that SqueezeNet is doing better over and above other pre-trained models. We feel that one reason could be that the delayed downsampling in the architecture of the SqueezeNet is aiding here in giving us the highest recall rates. And moving forward, we have used central kernel alignment and index that measures the similarity between neural network representations of a RGB and thermal gallery of a given data set. So these are the set of pre-trained models which are doing better among all the previous models. And so we have considered these moving forward. So when we have evaluated the CKA, we have seen that SqueezeNet is having the higher similarity rate over all the datasets that we have used, meaning that the feature representations of an RGB gallery is much closer to the feature representation of a thermal gallery of a given dataset using SqueezeNet model. And moving forward, we have used centroid condition to understand the model's ability to distinguish visually similar locations from dissimilar locations. So for an example, if you say, here we have used temporally correlated datasets, meaning that say if we wanted ideally the centroid feature representation of this location to be closer to the centroid feature representation of a same location in the opposite domain and far away from other locations. So with this condition, we have evaluated the pre-trained models efficacy, and we have seen that SqueezeNet is able to retrieve 32 locations correctly out of total 42 locations, and we have seen other models are doing relatively less, and we have seen that the baseline is giving 35 locations out of 42 locations. And so moving forward, we have used qualitative evaluation using distance plots. So ideally, in a distance plot, we want ith query image to have lower or minimum distance with the ith reference image in the thermal gallery. But then if we see different models, we have seen that each and every model is giving us minimum, but at a wrong index, I would say. And we have seen that SqueezeNet is able to retrieve the exact correct index from the thermal gallery for a given RGB query. And this behavior has been repetitive under different samples and on different datasets as well. And these are the top at one retrievals by different models and at different scenarios. So if you see, this is a low level illumination setting, this is at adverse weather condition, this is at high illumination setting, and at again a low illumination setting. So in most of the cases, we have seen that despite the temporal correlation that is present in the RGB thermal datasets that we have used, we find that SqueezeNet is able to retrieve exact same match for the given query image. And where the SqueezeNet is failing, we have also seen that all other models are failing. And so moving forward, we have used heat maps to understand what exactly the model is looking into, meaning that for making the decision. So here, if you see, the column 1 represents a query image and the ground truth image, and the column 2 here represents a saliency-based similarity map for the given column 1 pair. And the column 3 here represents a query image along with the top one retrieved image by the respective model, and the column 4 represents their respective SVSM map. So ideally, we would want the model to look into the major part of this image, meaning say the road here. But then we see the models are looking at some different aspects, and we feel that this is resulting in their unreliable behavior. And we see that SqueezeNet is more or less looking into the major part of the image. And so coming to the conclusion, with the given challenge of unavailability of VPR like RGB thermal datasets, we have chosen to evaluate the existing pre-trained models which are trained on RGB data for different on different tasks for RGB thermal retrieval. And interestingly and surprisingly, we have seen that some of the pre-trained models are doing well cross-domain generalization. And we have also seen that SqueezeNet is being as a clear standout in various qualitative and quantitative experiments that we have conducted. And when we have done the parameter comparison, we also have seen that SqueezeNet is taking like very less number of parameters, which could be an ideal solution in a real-time application where there is a resource constraint. And we also emphasize on the lack of BPR kind RGBT data sets. And the future scope, we would like to explore the early CNN layers, and then we also would like to explore the recent vision foundation models for image retrieval tasks. Thank you.
Great, we have time for one question. Anyone? Okay, then I have a question, and is that like, are you planning to also release like maybe data set and fix the thing that there is no such data set?
Yeah, we have a plan, but then yeah, we are working on it.
Yeah, great, thank you.
Thank you.
Now, I think there should be a break. There still will be a like 5-minute break between competition, mostly like for biological reasons. Like, but it would be just 5 minutes, not 15. Okay, and see you in 5 minutes for the challenge talks. They are like very interesting, not much worse than papers, or actually better maybe. Yeah. Okay.
Very good.
Okay, now you can go.
Okay. So before start to present in detail the challenge and the result, and I want to thank again the sponsor Google and the CTU in Prague for giving us enough money to get a good price for the best competitors. And now, what's new in this last edition of the challenge? Well, as Dimitro anticipated, we are now on a hexathlon. That means that instead of using the usual categories we have in dataset and common dataset, we try to enlarge these categories. We have 6 overlapping categories, overlapping because some machines can belong to different categories. We have the usual historical preservation, night versus day and temporal changes, aerial and aerial to ground images, symmetries and repeated structure. And for this time, we introduce more scenes with natural environments and transparencies and reflections. In the next slide, you will see more than 6 categories, 8, just because we split for the analysis night versus days and temporal changes, as well as aerial and mixer aerial ground, but these are the main. Also, we introduce a new evaluation matrix with respect to the previous one. This is in some way more clear to understanding this geometric meaning. It's just we align the cameras and then we compute the error of the reprojector with respect to the ground truth cameras. And this kind of evaluation also allows to have only one threshold for the evaluation, for setting the different accuracy in the matrix, instead of using 2 thresholds, one for rotation and one for translation. And if always go well, that means that we start with the structure for motion, we have rotation and translation, and then we compute the camera centers, this should be good. Here there is just the training set split in categories. Actually, as I said, temporal changes and illumination go in together, but it's much simple to draw a square. So, and also for the analysis. So you can see here the training set with the split. And as you can see, we can go further in division. We have on one side the transparent objects that go well with the symmetries and repeated destructors, while there are the other stuffs that go together, especially historical preservation with aerial images and the natural images with temporal changes and illumination. Here there is a sample of the superset from which some scenes were extracted for the test set for natural environments. And you can see there is a lot of variation in temporal changes, also in the illumination. And the scene structure is not the typical building, so there are less planes inside. And on the right, you can see also the sparse 3D reconstruction from the original super model that has about 3,000 images. And on the top right, you can see the best resolution, the best submission results after the alignment with the ground truth. And in this case, it was sufficiently well, but there are some points identified by the red and the green that are outside. Now for the transparent object, this was really a challenge, not also for the competitors, but also for us to provide a good, reliable ground truth. So since it's difficult, what we do was using a turntable and then acquire images on distributed of this ring. Well, you can see on the top right, there is the result for these categories, and using the new metric, the first two compare scores are quite high, while with the other metrics are low. That's because in the end, the top score get the correct camera center, because what in practice they do was to distribute along the ring the cameras and obtain the correct camera order. So the camera centers were correct, but they got a wrong rotation matrix. You can see here in some details, the blue is the ground truth, and the round one is the ones activated. And in some way, the top submission trick for the original aim of the post estimation. But if we focus on the aim of the challenge, it was to estimate the correct cameras if they were right, and also because these two methods were able to provide the exact image order. By the way, for the next edition, we are working for fixing this in the new metric. Now, here there are the results as taken from Kaggle for the top score. You can see again that the leaderboard is quietly determined by the transparent scenes here. And now going in more detail, if we also do the same using the previous metric, we can say that there is some movement in the leaderboard, in the rank of the leaderboard. And so here there are, considering also the old metric, the best competitors, and we have got VGG structure from motion, ZJU 3DV, and Motono as the third best one. By the way, the current energy voltage that it was the top rank in the new matrix score quite good also here. And so you can see is the fifth ranked. And now here there are the details of the result for the different categories. And there are 3 slides. Each slide put together the categories with high overlap. And you can see here that with the exception of the transparent image, considering a transparent image, because here there are no transparent image, the 2 metrics correlate quite well. And in this case, for historical preservation and air-to-ground images, here there are the top scored methods. And we see again that VGG structure for motion, and in this case, dense match and motono, but also current energy voltage seems to be the best for this kind of a category overall. While for the nature, temporal, and illumination split, here, this is in the original the designation design one single category, but for the analysis, here we split again in 2. Here the results are quite similar, and but there is no this dense match as the best one, but JU3DP and VGG, SFM, Motono, and current energy and voltage. And finally, for the transparent categories, that means transparent image, but also with symmetries and repeats. Here the result is more or like similar to the one of the this slide here. So this analysis also be done to give a reason how the challenge task was selected. And I think we can start then with the presentation, with the talk. Or if there are some questions, I don't know.
Yeah, so first of all, congratulations to all the winning teams. And I guess everyone here will be curious about how they make it. So yeah, let's first invite the first winner, current energy voltage. The teams here. I guess I will need to share my screen, right?
Okay. Hello, everyone. It's a great pleasure to come here to present our solution, first place solution on Kaggle. So let's start with the architecture first. So basically, we emphasize 2 different components in our pipeline. So the first one is the feature extraction and matching stage for non-transparent scenes. And the other component is image pulse estimation stage for transparent scenes. You already know what the transparent scenes mean and what the non-transparent scenes mean. So let me just go next. So for the matching stage, we have different images in the scene. Some of them are not rotated, not in a natural orientation. So we fix this orientation, aligning both images in the image pair, and we feed all the image pairs to the matching stage, to the multi-scale crop. So we extract the matches from the entire image, as well as from the cropped regions. And finally, we assemble the matches and we use them for submission.
And in more detail, we use the L-light detector and the light glue matcher with a limited number of the points. We also use, similar to the previous year, we also use key points and descriptors cache. It helps to reduce the time execution. Another finding that we developed is the multiple GPU acceleration. We found that we can reduce the time running significantly using both T4 GPUs on Kaggle with a mixed precision enabled. Also, we use the different scales for the images. So the best combination is 1080 and 2048. It was also useful to employ the repetitive scene reconstruction to address scenes with a low number of registered images. Together with that, we applied the horn alignment to estimate the transformation matrix. And the final thing is the OmniGlue, which is going to be presented on the CVPR later. So we got the best private submission with this model, but didn't sell it. The validation for non-transparency is as follows. So the best cross-validation score is 27% across the training dataset, and the best leaderboard score on the Kaggle is 28. So these scores are the best across all teams on the Kaggle. So you can see that the best cross-validation score is an ensemble of multiple of images scaled at different resolutions. So it's quite big. But for the best leaderboard score, it was enough just to make to use two scales. The interesting part and the main contribution in our work, I guess, is transparent scenes. We realized soon that we cannot use the conventional SVM method with the matches and call map for the transparent scenes. It just didn't work well. So our assumption is to compute the pose for each image in the scene and measure the rotation metrics directly. So this is the trick that was showed in a previous talk, and it helped to boost the score significantly. So our idea, the final idea is to compute the pose of each image to be located on a perfect circle with a equal space between the images. So the basic pipeline is first, we have to find neighborhood images. So the images that are similar to each other. So the first approach, so we try the optical flow, the grayscale, pixel level difference, the structure, similarity measure, index, and the number of matches. The best score that we got is 9%. For the cylinder, it's 92, and for the cup, it's 62. So the general pipeline is to compute the similarity for each image pair, get the distance metrics, get the shortest path between the images, solving the traveling salesman problem. After that, we can place the images in the right order around the circle. And finally, we get the rotation metrics. That's all. The interesting fact that we developed the second approach, and the second approach actually doesn't use this trick with the rotation metrics. So basically, we had an assumption that we assumed that we can order the images by looking at the number of the matches. So the number of matches tend to be higher for the previous image and for the next one. And also we use the high image resolution to extract all the differences in these transparent objects. So the highest resolution for the transparent objects, it was about 4,000 pixels. And this approach gave us 3% accuracy. So the cylinder is 77 and the cup is 41. So we iterated different ideas. Some of them worked on the cross-validation, some of them didn't work, which is the multi-crop, different detectors and matches, different kind of the models for the image retrieval, different refinement methods, non-max suppression. We also tried to run the disambiguation methods, but we did not find a good score for these methods. We also applied the so-called 3D ransec cleaning to eliminate the incorrect matches. And the final is the motion deblurring. So some images in the non-transparent scenes had blurred images, so that's why we try to eliminate this artifact. So finally, we got the best public and the private score on the leaderboard on the Kaggle. We got a huge score with the transparent trick. The execution time is just less than 5 hours, while the maximum limit on the Kaggle is 9 hours. And the total number of submissions is more than 300. Yeah, thank you. Yeah, this will be the last slide. So I did not cover every detail of our solution. So if you have any detailed questions, just go by this link and check out. And I'm ready to hear any questions.
Okay. Do I understand it right that you figured out that in the training set everything was on a rotating table? You believe that this will be the case, the case in the test set, and that's the biggest. Like this is what made you the best.
Yes, that's right. The interesting fact that all the images in both, I guess, in both transparent scenes were already sorted. So if you run, if you just use the same order as the images are sorted in the folder, in the training folder, and compute the rotation matrix, you already get a high score. That was a signal for us.
Yeah. Any other questions? Yeah. So thank you for the presentation.
Thank you.
Yeah. So let's invite the second team. Okay, let me reopen.
Hello, everyone.
So the second one provide the video, is that right? Okay. Where is the video? I find video.
So like we just open this, right? Like you just show this guy and then okay, so now like try to open again where it is.
Hello, everyone. It's very pleasure to present the second place solution today. We are the location team from AutoNavi Alibaba. Our team members include Wang Shengyi, Sun Yikun, Chen Hao, Ma Yunchao, and our mentor, Zhang Tao.
Oh, let me share the screen. Didn't share the screen.
Here is an overview of our solution. We started by designing a new global feature that adapts to the scenes, generating stronger representations for downstream tasks. For regular scenarios, we created an iterative optimization scheme for structural motion based on the minimum spanning tree. This approach uses concise data associations to build a reconstruction model skeleton. And then we add redundant associations to iterative enhance the model's accuracy. For transparent scenarios, we hypothesize that the camera captures images by rotating around the transparent object. Therefore, we simply transform it into ranking task and directly output the appropriate poses along the circular path. Specifically, we first constructed a stronger global feature for image retrieval. Our basic idea is to adaptively enhance the discrimination within a scene. This is important for retrieving highly similar samples. Another intuition is that mismatches caused by repetitive textures might be better addressed at the retrieval stage. Therefore, we aim to further enhance the semantic strength of global features by introducing stronger semantic elements. Guided by these motivations, we first extract point features and patch features from an image using allocated and de novo tool. Then, we concatenate the patch features to the point at each corresponding location. And finally, we generate a global descriptor based on the clustering and the valid algorithm. It is worth noting that the clustering provides a mechanism similar to fine-tuning the backbone. Additionally, since patch features inherently possess stronger semantic than point, we directly introduce de novo tool to further enhance the semantic effect. In our tests, this method outperformed state-of-the-art technicals such as NetValid, Analog, Dino, and Salad. Without considering transparent scenarios and with all other configurations being the same, our method also outperforms NetValid on IMC metric. We will discuss its further impact in the following sections on MST-aided SFM and transparent scenarios. Our approach for local features involves an ensemble of multiple feature detectors and matchers. We experimented with combinations of allocated, superpoint, and DUSt with disk and SIFT. We found that the V2 version of the DUSt detector produces richer and more evenly distributed feature points. This provided us with the best score. In the data association phase of SFM, extensive feature matching is typically undertaken to enhance the robustness and the accuracy of SFM. However, increasing data associations in scenes with repetitive textures can result in more incorrect matches. This issue was evident in the reconstruction result of church scenes in the training set. In the left image, the front and the back of the church were incorrectly matched together due to similar textures, resulting in the back of the church failing to register any images in the direct SFM pipeline. As the contrast, our MST-aided cost-to-fan approach effectively resolved this issue. So on the stage 1, we built a similarity graph with images as nodes and similarities as edges. The MST from this graph provides optimal data association for the initial SFM. The left image shows the nodes 1 to 8 forming an MST path around the church, separating similar images 1 and 8 in the tree. On the stage 2, we use initial camera poses from stage 1 for geometric verification, filtering incorrect matches and refining the model. This approach keeps stage 1's cost benefits while improving the fine accuracy. Finally, the two-stage MST-aided SFM helps us achieve an improvement of nearly 2 points. For the transparent scenes, We also use global features to generate a similarity graph. When calculated the mean cost path to determine the image shooting sequence, arranging all images in a closed loop to determine their positions. Interestingly, the TSNE visualizations of a cylinder's global feature revealed a highly ordered 2D layout, significantly aiding in recovering the image capture sequence. Eventually, the solution for transparent scenes improved scores by nearly 6 points. We also tried some methods that didn't work as well. For example, we attempt to add a few redundant edges to the first phase of the MST to balance the recall and precision. This method achieved a good private scores but didn't improve the public score. We also tried dense meshing methods like the LoFTR series and the optical flow, but the results didn't meet our expectations. Additionally, due to time constraints, we didn't manage to try TTA and multi-scale matching technicals. Thank you very much.
What's here? Yeah, okay. Let's move the other team. Okay. So where are we here? Let me show you the download.
Should I share my screen? Oh,
you already have the PowerPoint? Okay, that's good. Yeah, maybe you can share your screen.
yeah, it'll be great. Could you first close the screen sharing so that I can share mine?
Yeah. Oh, it's screen sharing.
Can you see stuff and then PC looks like this stuff share?
Oh, okay. Yeah.
Yeah, thank you. Yeah, this here. Check. Could I start now? Oh, we need to wait for more. Does it look correctly?
Yeah, everything good. Okay.
Hello everyone. My name is Jian Yuan, and I'm a PhD student at the University of Oxford, Visual Geometry Group. We are glad to share our third place solution in RMC 2024. The solution mostly used our recent work with GGS-FM. The team members include me, Minghao, Chris, and David. Actually, to be honest, I'm a bit shocked that if I understand it correctly, does it mean we should be the first one if using the correct metric for camera pose estimation instead of camera centers? I'm still shocked, but let me introduce our solution first. Yeah, so we just finished our work on CVPR 2024, which has been accepted as a highlight. Basically, it is a fully differentiable SFM framework, and we trained it end-to-end. Specifically, given several frames as input, we first conduct point tracking to get some 2D correspondences. Then, we fit the image features and track features into a deep camera predictor to estimate all the camera parameters simultaneously. Finally, as in traditional SFM, we do triangulation and bond adjustment to optimize camera parameters and 3D points at the same time. Basically, we just follow the traditional incremental SFM pipeline and convert it to a differentiable way. The whole framework works quite well on various types of input data. And especially, as far as we know, it is the first time that a deep SFM method can outperform CoMap in phototourism data. You know, CoMap itself was specially designed for phototourism data. Let's have a look at some results. For example, on the test set of RMC 2021, it is also called RMC phototourism dataset. There's a clear performance gap between the CoMap-based methods and the deep methods like post-diffusion. We observed that the main performance difference is due to joint optimization. Although these deep methods have their own joint optimization steps, they did not work that well as traditional BA. Therefore, we designed WGGS-FEM as a whole pipeline that with all components differentiable, including the joint optimization. As you can see, compared to previous deep methods, here, our, for example, 12 here, our performance jumped a lot, such as AUC at 3 degrees, improved from 12 to 62. It achieved total results among all the methods, no matter the deep one or the classical one. You can see the clear jump in all the metric. And here are some qualitative visualization of the reconstructed scenes. The left is RMC 2021, and the right is Core 3D dataset. Here's just a brief visualization, and if you need more visualizations, you could visit our webpage. We are encouraged to test our method on RMC 2024. Okay, let's go. I first had some trials in my local machine, and it works quite well. A light plus light glue seems to be the most powerful combination in RMC 2024, while in my local machine, WGGS-FEM works clearly better than COMAP plus light glue, with an AUC against with an AUC 0.27 against 0.24. We had a good start, but the bitter lesson is I was spoiled by meta cluster. We are required to run our code on the cargo cluster for RMC 2024, whose GPU is at most 16 gigabits instead of 80 gigabits. Actually, it's our fault that I should notice this earlier, that most users do not have a high memory GPU. So I think the such a constraint from the cargo cluster is reasonable. I mean, 800 GPU could be a luxury for most people. So what can I do? Learning from my trials for RMC 2024, I'm developing a low memory version which seems to save the memory by half. I hope to release it within this month, although sometimes I'm just lazy and sometimes the stuffs are out of my control. And the second option, which is also the one we used for RMC 2024, is combining COMAP plus WGGS-FEM. We have 3 ways to integrate WGGS-FEM into COMAP pipeline. We can use the point tracking module from WGGS-FEM to provide more tracks for COMAP. We can refine the SFN tracks, which were built by COMAP. And we can use WGGS-FEM to get the camera poses of the unregistered images. These 3 ways improved our public score from 0.17 to around 0.20, saved us from a ranking of around 50 to top 3. I mean, in public leaderboard, we are, in the private leaderboard, we are third, using the camera center metric. So the first way, additional tracks. For each input frame, we view it as a query image and find several nearby frames. By this, we can track the 2D points of the query frame and look for their corresponding points in the key nearest frames. Then we feed these tracks into COMAP as matches. We believe this is helpful because a well-known topic in SFM is how to chain 2D pairwise matches to a track, and such chaining cannot be guaranteed as accurate. This is widely observed in a lot of experience we have conducted. So we think directly searching for tracks is quite beneficial and complementary. This hypothesis is verified in RMC 2024. And we are glad to say this is efficient. For a scene with 50 frames, it takes fewer than 2 minutes, totally acceptable for our RMC 2024 solution. The second way was inspired by the winner solution from the DUSt3R waiting last year. In WGGS-FEM, we use a cost-to-find strategy for point tracking. For example, with some, as can be seen here, we first attract some coarse tracks over the image level, over the whole image. Then we crop the patches with a size of like 30 by 30 around the coarse tracks and refine the point locations within this range. It means if we run, I mean, at the same time, if we run COMAP, it will have some sparse 3D points and the corresponding 2D projections. These 2D projections are actually SFN tracks, and they can be refined by our fun tracking module. So that's what we do. And in our cargo submission, we only refine the 4K SFN tracks for efficiency, but it is good enough. Refining each track will take around 0.03 seconds. So for each scene, it is around 90 seconds in total, acceptable for us. And the good news is we can do this easily and totally in Python. We do not need to recompile COMAP for it. I believe that in recent years, users are afraid of modifying C++ code or compiling by themselves. Yeah, I think this is important for a lot of usage. And the third way is quite straightforward. We all know that COMAP usually cannot register all the images of a scene. So we use WGGS frame to localize those unregistered frames. The general idea is for each unregistered frame, we can find some close frames that have been registered by COMAP. Given this, we can build a small subset and run WGGS frame over it. Easy and served. But sometimes the unregistered images may be too challenging. If so, we skip the bound adjustment step in WGGS frame and only pick the predictions from the deep camera predictor. Once again, we ensure the whole process is fast enough. For each unregistered frame, it will take only 3 to 5 seconds. And the number of unregistered frames will not be too much. Yeah, overall, such integration works well. It is very happy to see our method can really work in RMC 2024, whose data is totally unseen to WGGS fan and a super challenge. But personally, I still hope to try using WGGS fan only in the challenge next year, RMC 2025. So thanks for listening, and thank you again to the organizers for this great challenge. This has become a standard and mainstream benchmark in matching and SFN. I would say it is a fantastic job. And yeah, one more thing is, we are going to present our poster this Friday morning. Chris and David will be there to present the poster. I may also be there, probably in an iPad or laptop if the internet connection is good enough. So feel free to say hi if you have any question or want to discuss any topics there. And feel free to send us an email or create a GitHub issue. I check GitHub issue every day. Thank you, and question time.
Thank you for the presentation. Any question? Yeah, I'm sorry to hear that you can only use the iPad.
No worries.
No, yeah, since there's no question, yeah, maybe I have a simple question. So do you have any insight to make, your awesome WGSM more time efficient? So like, do you have any insight, like, how much room left for you to improve the time efficiency?
Yeah, the question I heard is about the time efficiency, or is it about the memory efficiency?
Well, like maybe both memory and space. It seems your method have larger footprint in the memory, and also looks like more computation intensive, right? If I understand correctly.
Yeah. First, regarding the time efficiency, yes, we do believe there's a lot of room to improve because for simplicity, I keep all the code and implementation totally in Python, which means, okay, it will not lead to maximum speed. And an idea here is that probably we can write some like CUDA kernels or something to accelerate it a lot. And another way is currently we use around 4K tracks for each core frame. I personally believe this is too many. Probably we can reduce it to quite lower number, and which means ideally we can further reduce the time for inference. Yeah, this is for the first question. And regarding the GPU memory yeah, this is a big problem. I did learn some lessons from IMC 2024, and I hope we can release a new version quite soon. It will save the GPU memory by half. But even by half, it is still not that friendly. So I hope we can solve this in the second version of VGGSFan. A potential solution is that we can modify VGGSFan to like kind of closer to traditional SFM, which is divide and conquer, or a cluster by a cluster, a group by a group. By doing this way, we can further reduce the memory consumption there. I hope this can serve some concerns. Thank you.
Yeah, thank you for the answer, and thank you for the great presentation again. Yeah.
Stop the screen sharing and give it to the next one.
Let's move to the other team. I guess the other team is the ZGU3DV. Is any like author here, or are they remote?
Can you hear me?
Oh, you're in the room? Oh, great.
Yeah, yeah.
You want me to share the screen or you share screen?
I will share my screen.
That sounds great. Yeah. I guess you can share, right? Like, yeah, go ahead.
Can you see my screen?
Yeah, yeah.
Okay.
So
Okay.
I guess you can go ahead.
I will start it. Hi, everyone. We present our sixth place solution in IMC this year. Our team member in this competition includes Hao Yu, Xin Yihe, Dong Litan, Si Dapeng, and Xiao Weizhou. Here is an overview of our pipeline. For general things, we continued the winning strategy from our IMC 2023 solution using DF-SFM, a two-stage and a hybrid matching strategy for robust matching. I will provide a detailed introduction to DF-SFM later. For transparent scenes, we identified the patterns in the camera trajectories for transparent scenes in IMC 2024. By assembling the camera center positions on a circular trajectory and then recovering the order of each image, we were able to estimate the 3D poses of the images. Let's first talk about our solution for general scenes. In the matching phase, we first construct image pairs by the global descriptor. Then we detect image rotation by performing a lightweight sparse key point detection and matching on rotated image pairs. The pair with a max number of inliers are used for the next stage matching. Based on the rotated pair and the first stage inliers, we crop the overlap region and resize the image to align the scales. Then the second stage of matching is performed using both detect-based and detect-free matchers. Last year, when we used the semi-dense matching model such as LoFTR, the cost-to-fine matching process of LoFTR resulted in the multi-view inconsistency problem. This year, we adopted dense matching models such as DKM and ROMA. Although the matches generated are all at the pixel level, since DKM and ROMA sample matches from flow, they also have the multi-view inconsistency problem. Therefore, we also addressed this issue through a cost-to-fine architecture. Okay, in cost mapping phase, our idea is to sacrifice match accuracy for consistency by match merge and reconstruct a cost model. Then we improve the pose and point cloud accuracy by our iterative refinement pipeline. In the cost SFM phase, we first aggregate matches of each image by its matching pairs. Then, for each image, we perform NMS over aggregated matches and merge matches to the point with the max match confidence. We reconstruct the cost model based on the merged matches. Then, given the cost model, we refine it for higher post accuracy by our iterative refinement phase. Our idea is to iterate between multi-view matching refinement model to refine feature tracks for higher precision and use geometry refinement to improve process and point cloud accuracy based on the refined tracks. Next, let's dive into feature track refinement module. The inputs of this module are coarse 2D locations of feature tracks, and the outputs are their refined 2D locations. Features of corresponding image patches are extracted and transformed by our multi-view feature track transformer. Then tracks are refined by the multi-view feature correlation. More details can be seen in our research paper. Here are our results. We used superpoint plus superglue for sparse matching and ROMA or DKM for dense matching. Due to the original ROMA being too time-consuming, we replaced the feature extraction backbone of ROMA with VITB and retrained a model. The results showed that our retrained ROMA could achieve better results. However, we found that on the leaderboard, our scores are quite low. We believe that the transparent things are the cause of this issue. So we have tried to process the transparent things with special methods. By observing the characteristics of the camera center trajectory in local transparent scenes, we designed a specific strategy for transparent scenes, that is, generating a circular camera trajectory and recovering the order of the images. The first problem is how can we distinguish these transparent scenes on Kaggle? We use the token card, which is a segmentation model, to perform foreground segmentation on each image. If the foreground areas segmented from all images are roughly consistent, it indicates that the camera trajectory for this scene is approximately circular, and we mark this scene as a transparent scene. And the next step is how can we recover the image order for transparent scenes? We designed a strategy based on the image similarity matrix plus TSP algorithm to recover the image order. The key step is to estimate a similarity matrix that is closest to the ground truth. We tried two methods. The first method is using a retrieval method such as NetVLAD to calculate the global feature similarity of images and build the similarity matrix. The second method is employing a sparse matching with ransack approach using the number of matches generated between two images to represent their similarity. Here are our results. If using a light with nearest neighbor matching to recover the image order, we achieved the highest score of 0.225 on the public leaderboard, which ranked third, and the private leaderboard score of 0.191, which ranked sixth. Regrettably, although the strategy using SIFT with nearest neighbor matching to recover the image order only scored 0.207 on the public leaderboard, it reached the highest score of 0.201 on the private leaderboard, which ranked fourth. Okay, that's all. Thank you for your listening.
Thank you for the presentation. Any question from the audience? Yeah, maybe I can ask a quick question. So what are potential works to improve, the pipeline? Can you say something about this?
This job, I mean, DFSFM is done by my teammate, Xingyi He. In my opinion, I'm new to this competition as a member of their team. So in my opinion, I mean the feature of SFM or the improvement of this pipeline should be turned to such as VGG SFM. We need to do end-to-end optimization to make our model more robust and less affected by noise.
Yeah, thank you for the answer. Yeah, thanks again for the presentation. I guess now let's move to the last team.
Okay, I will stop my sharing. Thank you. Thank you very much.
So the last one and one view. Only video? Okay. Yeah, let me share my screen.
Hello everyone. Today I am presenting my solution that secured the 8th place in the image matching challenge this year. Let's dive into the details. This slide provides an overview of my approach. I started by finding similar image pairs for image matching. This solution involves 2 stages of image matching using a light and light group model. The stage involves various transformations and a pin transform to enhance key point detection. Additionally, I performed the reconstruction using multiple model cameras, including simple radio and simple pinhole. Finally, I selected the largest map and extracted the camera position and orientation from this map. This slide explains the process of the first stage of image matching. First, I focus on the problem of rotation tolerance with a light and light group method. I executed image matching on the original image and their loaded version. According to the central plot, it was observed that the number of matches key points dropped significantly when the images were rotated between 45 and 60 degrees. To address this problem, I adopted the TTA processing by rotating the image by 90 degrees. I performed the image matching by rotating one image to 0, 19, 118, and 217 degrees, then concatenated these key points. This slide explains the process of the second stage of image matching. In this stage, I enhance the number of key points by correcting image rotation using a pin transform. First, from distribution of key points detected in the first stage, I calculate the bounding box right green and crop image 1 with bounding box. Next, I estimated the homography matrix from the key points. Using this estimated matrix, I apply the pin transform to image 2 to correct its rotation related to image 1. I then apply image matching to the corrected images. Through this process, I observed the increase in key points by a factor of 2 to 10. Here, I present an example of several images. On the left are the original image pair, and on the right are the transformed image pairs. The first example is an image of a building hidden behind the tree leaves. The second is rotated loading, and the third is aerial images. In these cases, I confirmed the pin transform using the homography matrix could correct the image rotation and result in an increased number of key points against the first stage. This slide explains the reconstruction process with a column. I noticed from the ground truth data of training dataset that 2 types of camera model are used: simple radio and simple pinhole, as summarized in the table. Therefore, I execute the reconstruction using both simple radio and simple pinhole camera models. From the maps generated by both models, I adopt the map with the largest number of images. This slide highlights the performance improvement achieved through my method. I started with a baseline MAS score of 0.1544. By incorporating TT and rotation 90 degree and image matching first stage and rotation correction in the second stage, and reconstruction with marriage camera model, I incrementally improved my score to 0.1799 on the private leaderboard. That concludes the explanation of my approach. I extend my gratitude to the competition host, Kaggle staff, and the public notebook contributor for their support. Thank you for your attention.
Yeah. Yeah, I guess it's time to wrap up our workshop. Let me share the. Hey, where is the slides? Where's that?
Yeah.
Okay. So yeah, sorry. Actually, it's not. I didn't make the slides, so I can just try to yeah, read the slides. Sorry. Well, what's next after this workshop? First of all, each error metric has pros and cons, and we are thinking about how to improve it. And also, we are wondering if we can truly do the large scale, because large scale Sense now has 100 images to allow evaluation and running time compatible with Kaggle constraints. And third question we are asking is that should we move to an open benchmark with open data? This would probably lead to wider spread and community collaboration and support, including issue detection and fixing, as well as new and better image matching challenges and solutions. And of course, we always, like to have like a roundtable discussion. And yeah, please, send email to us here and let us know. And thank you all for the like joining this workshop. Yeah, so that's it. Okay.
Please stop recording.
Recording.